Okay.
All right, great. So my name is Paul Rosen. I work at the Jet Propulsion Laboratory in California. I am sort of the designated lead for this class on InSAR training using ICE, MintPy, ARIA tools, and OpenSAR Lab. Many of you have, I believe, have participated in our pre-course introductory segments and some of the office hours. So some of this introductory material will be repeat for you, but for those who haven't, we need to at least introduce the people who will be teaching this class. So first, I'd like to say welcome to all of you. Thank you for signing up for this class. The instructors have worked pretty hard over the last several years putting together a cloud-based instruction tool that uses resources on the cloud for processing and teaching that we believe is at least a prototype, if not the actual future for computing using InSAR data. So we believe you're going to get quite a bit out of this class. Last year's class was done in a similar format, and we thought it was quite successful. We've learned some lessons from that and have incorporated those this year. So we look forward to this week. We do hope that you've looked at the pre-course material as we asked you to do, because a lot of that is, I think, somewhat essential to making the most out of this week. But be that as it may, as you all know, Sentinel-1 is producing an enormous amount of time series data at C-band right now, and there's a constellation of over 20 SAR systems in orbit. Not all of them have quite the data policy and coverage that Sentinel, but there's an enormous amount of data available. In the future, there'll be missions like NISAR and Rose-L, ALOS-4, continuity for Sentinel. That is just a very promising future for the ability to look at long-term time series of SAR data for geodetic applications. So we believe this is a great time to be learning about these techniques and be ready for the future. So in addition to me, we have a number of other instructors in this class. Some of them are probably on today. Some of them may not quite be on yet. Some people will be popping in for their lectures, but we'll introduce them anyway. Now, just a little bit by way of background, I've been working at JPL for the last 30-ish years, and I've been doing InSAR technique development for many of those years. In the early years, a lot of the base software that this course is based on was developed by me and a bunch of other people here. The tools that you're using in this class have largely been developed by successors to those initial developments, and they're very powerful tools. So next, Gareth Funding, could you just say a few words about yourself?
Hello, everyone. My name is Gareth Funding, as said. I'm a professor at the University of California, Riverside. I have been doing InSAR since the year 2000, which is almost half of my life. And I mainly focus on applications of InSAR to tectonics. I study earthquakes, I study the loading of faults, post-seismic deformation, and fault creep. And my part in this workshop is mostly to cover the material where we talk about modeling. And I hope to see you all throughout. I'm looking forward to this.
All right, thank you. Franz.
Hello, you all. Franz Meyer from the University of Alaska Fairbanks. I'm a professor here for remote sensing at UAF, mostly teaching microwave remote sensing, but also optical topics. I'm also the chief scientist of the Alaska Satellite Facility, and the data sets that you mostly will be accessing today, those are located at the at ASF. ASF is the data center for SAR data that's operated by NASA, and it houses a copy of the global Sentinel-1 archive, So in addition to ISCE, we are a complete global copy of that archive. And we also will be the data center for ISCE, which is coming in 2023. I think is particularly useful for InSAR analyses. We may touch on that here and there when we talk about things like coherence, but also ionospheric errors and other things. You'll hear about the benefits and the promise of L-band. Like Gareth, I also have been doing InSAR since 2000, with a focus initially mostly on methods development, on things like atmospheric and ionospheric correction. In the last few years, pivoted a bit more in the direction of hazard analysis and hazard monitoring. Thanks.
Thanks, Franz. The next instructor I see on the list who is actually here, I think there's only one more, and that would be Yunjin John. Can you introduce yourself?
Hi, everyone. I'm Yunjin John. I'm a postdoc at Caltech. I'm working on the InSAR time series analysis and the InSAR application on volcanoes and earthquakes. In this workshop, I will mainly help you to walk through on the mean pi part for the InSAR time series analysis, and also help you to demo a little bit on the stack processor, which is an alternative choice for the area tools to generate the stack of interferograms in preparation for InSAR 10 series. Thank you.
Great, thanks, Yunjin. The other four instructors, being very busy people, will pop in when it's their time to instruct. Many of them actually developed the modules that they'll be teaching on. Haresh Fatahi is at JPL, and David Beckert, also at JPL, both instrumental in the development of tools for modern InSAR time series analysis. Scott Hensley helped develop many of the early techniques and helped me develop the math module that hopefully you all took a look at, the math basics module. And Brent Minshew is a professor at Massachusetts Institute of Technology, has done a lot of work with InSAR on glacier motion. And we've added a couple of modules this year that he and I think one of his staff assistants, Brian Reel, will be teaching this year. I think it's either Wednesday and Thursday. So a large staff and very eager to get going. Also, we have asked 4 of the students who volunteered to be TAs to participate. They will be helping coordinate your homework, looking at it, grading it, dispositioning it, and also hopefully answering questions along the way. And so far they've been in the pre-course, they've been quite helpful. So we thank them. If you could quickly introduce yourself, if you're on, Luyen Bai, I think I saw Luyen, could you just say a few words?
Thank you, Paul, and nice to see you again in the main course. My name is Luyen Bui, and it is now doing my postdoc at the University of Houston. I did my PhD in InSAR time series optimal design and deformation time series analysis before, with experience in applying in using ice, giants, and stamps. So I registered to be a TA here with my experience, and I joined the course to in order to update the use of new ice and mean pi. Thank you.
All right, thanks. Sorry for mispronouncing your name. I wrote it down wrong on the piece of paper here. Okay, next would be Shubha Mawashti. Can you say a few words?
I'm Shubham. I'm working as a PhD student in Indian Institute of Technology, Roorkee, India. And right now I'm working on microwave remote sensing time series monitoring of urban areas, how the deformation and what are the reasons for various reasons for the deformation. I did my master's also in the microwave remote sensing. And right now I'm the TA in this ISCE course 2021.
Great, thank you. Faizan?
Hi, good morning, everybody. My name is Faizan Sabir, and I'm from Pakistan. By profession, I am a geologist and I have a 10 years of experience, mainly in disaster management and groundwater. And I started working on synthetic aperture radar from 2017. Good to see you everybody here in the training. That's all from my side. Thank you very much.
All right, thanks. So you're a little quiet, Faizan, so maybe work on turning up your microphone for the next time. And I think the last TA who I have not seen online here, and I'm not sure, we haven't heard much from her this week, so I'm not sure what her status is. Pratyusha Kanuru, are you on? Okay, we may have lost her. Okay, so we have at least 3 TAs, and then there's, of course, our intern at UNAVCO, who's been really helpful and instrumental, actually, in getting this course organized, is Becca Bassard. Maybe Becca, say a few words.
Hi, I'm Becca. I'm a PhD candidate at the University of Oregon, and like Paul said, I'm also interning at UNAVCO this summer. And I do a lot of time series analysis with InSAR over different volcanic systems. So I'll just be around doing various tasks, trying to help out. So nice to meet you all.
Great. All right, thank you. So I think that's all the introductions of people. I guess I should also thank Melissa Weber, who is, I don't know if she's still on. She kicked off the meeting and started the recording. She has been critical to organizing all the logistics and getting invitations out and keeping communication up with all the students. So I don't know, Melissa, if you want to say anything about logistics.
Hi, Melissa Weber here. I guess if you have any problems with sound or closed captioning, we're trying to get that set up here as well. Any issues with the Zoom, just contact me.
All right, thank you so much. All right, so we're a little behind schedule as always whenever I do these things. So we're going to go very quickly over the course agenda, mostly for today, just focusing on today. In the pre-course, of course, we've done this several times, so you should, if you're confused about it, you can always go back to those recordings. The agenda is pinned in the Slack channel, so you should be able to find the link to it very easily. And in the agenda itself, once you get there on the Google Drive, you can see a bunch of other links. So we're trying to make it so that if you feel a little foggy about all the different things that we are offering and where the resources are, that there are multiple ways to get them, and hopefully will be helpful for you. Before we go anywhere else, I don't know, is Hillary on? I don't think I saw her. Hillary is our external evaluator on this program, and she has put together a pre and post course survey that is very important for you to do, for us to be able to evaluate the class. Our sponsors at NASA kind of insist on it. And so if you haven't taken the survey yet, sometime today, please go to this link that you see here and take the survey. There are detailed questions about InSAR there that you probably don't know, you shouldn't necessarily know the answer to. You may know the answer to some of them. It's important for us to get a baseline so that when you take the post survey, we can understand whether you learned anything or not, and I'm sure you will. So please do that, the pre-survey, as soon as you can. All right, so we've got these links, course summary, and I'll skip the workshop overview, which you can read at your leisure and hopefully have looked at already. And just focus on the agenda for today. You're on here, so you know the Zoom link. We're going over the introduction and the agenda. We'll have a very short recap of OpenSAR Lab for those of you who may have missed the training. There's a link here for the training if you want the entire course description for it. Then after a short break, we will begin in earnest with our training modules. The first one is to be given by Gareth and Franz on geophysical modeling. And after another break, we will go to discussion of INSAR theory and correlation theory that I will give. And then after another break, we will launch right into processing some strip map data that I am assuming Haresh will be leading. Then we'll have a short discussion of homework, and we will then adjourn for the day at 2. I have a hard cutoff at 2, so I'm going to have to leave exactly then. We do have office hours every evening from 5 to 6, Monday through Thursday, and every morning 7 to 8, Tuesday through Friday, and that's all Pacific time, where you can ask questions about the homework. On Tuesday and every other day, we do have an hour reserved at the beginning of the day for reviewing homework from the previous day and any problems you might have encountered. This can be you showing us your notebooks and what problems you ran into, you tweaking parameters and just showing new results. And hopefully everything will work well. We've gone through the notebooks, they should all work, but if you're having trouble, this is a place to debug them, as well as in the office hours. So in the interest of time, I'm not going to go through the rest of the agenda. We can go over that again tomorrow morning, day by day. Okay, so with that, I think I'm going to turn it over to Franz. If there are any quick questions, please ask them in the chat. I see there are some chats here. Group photo sometime this morning. Yeah, okay, that's a good idea. We can try to do that. That was a private message to me. Maybe during one of the breaks, we'll do a group photo. All right. Franz, you're up.
Yes. So yeah, I'm putting in the chat one more time the link to the OpenSAR lab. You won't need the OpenSAR lab right away, but if you, it's maybe a reminder if you haven't yet registered or created a username and password for the OpenSAR lab to do that now. So we will use a deployment of the OpenSAR lab that's available at unavco.asf.alaska.edu. So if you already have an account, you can log in now, and I can show you real quick what that would look like. This will stop screen sharing. Paul, can you surrender the screen? Okay. Let's see here. So let's find the right browser. Okay. So once you're logged in to your server, you should see an environment that looks like this. We've done some training earlier in this week to sort of explain to you how you get into the OpenSAR lab and how you interact with the notebooks and how you can navigate around within the OpenSAR lab. If you weren't able to attend this particular training, please go to the syllabus. Let me bring that over real quick. The information about the training is actually in the syllabus in 2 different places. There is early on the first page, there is a link down here that says how to use the OpenSAR lab training recording. Let me correct this capitalization here. So you can go to that YouTube link to get to that training. I also replaced the link down further down in sort of the pre-course content material. So if you scroll down a little bit, there is, if I find it, one on the OpenSAR lab. I missed it. Where is it? ISCE. Oh, here. So it's the, let's see, so there's needed math, that's one of them, the Python Unix plotting NumPy pre-event recording, and then here's the OpenSAR lab recording, and there's the video linked also here. So if you have questions about it, we can resolve those partly today, but you can also go back to this recording and sort of hop through the recording. You don't have to watch the entire thing, but you can sort of on YouTube maneuver through the video to the places, to the relevant places. So once you're in there, you should see this kind of environment. All the notebooks and all the presentations that we will do this week, they are all located within this folder called Geosync. So if you click on that folder, you see, once my screen refreshes, not sure why it doesn't. Can you guys still see me?
Yes.
It's not updating.
Is it not updating for me, or is it not updating for anybody else?
It's not updating for us. It just shows the geosync at the top, but you're still at the top level below it.
Okay. Let me see here real quick if my.
And
I mean,
you've got the spinning wheel up in the menu bar.
Oh, my server had shut down. Okay. Well, so if you go into that geosync folder, you see all the different, if you do that for yourself while my server is restarting. If you go to the geosync folder, you can see all the different modules of the syllabus. So if you sort of hold up the syllabus and the different folders in a geosync environment side by side, you can sort of follow through the different parts of the training. You see things like 0.1, 0.2, the 0 points. These are pre-recording, pre-event. This is pre-event content. And then 1.1, 1.2 is day one, and so on. So it nicely tracks the content of the syllabus. The individual units, they have notebooks. Most of the time, we will go through the material directly in Jupyter Notebooks. Starting, at least that's true for Paul Rosen's session later today. Sometimes the individual elements contain PowerPoints, so you can download those PowerPoints to follow along with the session that's going on live. So the first one that we will go through here in a little bit is 1.2, and that 1.2 session will have some PowerPoints that you can download, or a PDF document that you can download to follow along with Gareth's presentation. And then later on, we'll do a lab, which will be in the form of a notebook. And so, every day, have your OpenSAR lab open and available. I'm getting put right now in a different instance, so it takes a little bit for me to relaunch my server. So sometimes if you are on a node that's already running, it may take you like a minute, maybe, to start the machine up. If, like me in this case, I'm getting put on a different node, and then it can take anywhere from 2 to 5 minutes, basically, to spin up a new machine in the cloud.
So Franz, people seem to be getting kicked out. I got kicked out, and a lot of people in the chat are saying that they crashed. I'm relaunching my server myself.
Okay, yeah.
I don't know whether there's some issue with Amazon or what.
Yeah, I'm going to clarify that here in a second. Not a big deal. If you got kicked out just like me, you just restart your server. And we won't need the OpenSAR lab right away, because the first presentation by Gareth is going to be a PowerPoint document. But yeah, so once the server is up, usually, and if it's idling in the background, usually after an hour, the server is being shut down. So, if you have it up, make sure that you sort of refresh the screen off and on to prevent the thing from being shut down if you need it. So my service restarted, and yours should do as well once your system is back up. So anyway, so we will be going next into the section 1.2, Geophysical Modeling with InSAR and GNSS Geodetic Data. And I'm going to navigate here while you're waiting for your services to come online. And in here, you see that there's a PDF and a PowerPoint file for Gareth's lecture. So You might be able to open the PDF directly on the OpenSAR Lab. There you go. So you can follow along the PDF directly in the environment. If you wanted to look at the PowerPoints, you can click that radio button next to the PowerPoint and then click on this download button to download the PowerPoint directly to your machine. Once Gareth is done with his lecture, we'll jump into the notebook up here to do a little bit of an exercise in geophysical modeling. So hopefully your machines all are getting online again. I'm going to ask the team here in a second what may have happened, but it should all work out fine. If you don't have an account on there yet, please go to the environment and sign up for the environment. When you do sign up, please use the email address that was used when you registered for the UNAFCO course. So the email address you used for registering for the class, that's the email address you should use for signing up for the OpenSAR Lab. If you use that same email address, you are automatically whitelisted, and once you set up a username and password, you're ready to go right away. And so I'm going to monitor this while Gareth is talking. If there are questions, I'm going to address them in the chat and work with you to make sure everybody gets online. So I as a sort of a super user, I can also check how things are going. And I see that we have 77 people whose service is either spinning up, but they're all online. So most of you should be coming online here again in a few seconds. Okay, I think that's all I have. And so the server is back online, excellent. And I'll find out what the little hiccup was. Okay. Well, have fun in the class. I hope the entire environment works for you. I forgot to say, I mean, the reason why we use the OpenSAR Lab is because we have 150 students in this course. And the software that needs to be installed in the back end to make everything work and make all the notebooks work is complicated to install. And if everybody would install it on their local machine separately, it would be very hard for us to work through the different labs because there may be conflicts that each one of you runs into with the software that would be very difficult to resolve live with 150 people. I understand that a lot of you in the end will want to have the software locally. And so as we go through the training, toward the end of the training, we will give you some instructions on how to deploy the setup you see on the OpenSAR Lab on your local machine. So stay tuned for that as we go through the training. And with this, if you have any more questions, please ask them now, and otherwise I give it back to Paul.
So I think if you have 77 plus people attached, things seem to be working again, so that's good. And if there are questions, just put them in the chat. We can move on now to the first module. Do we have a break or not?
We did have a break scheduled.
Yeah, so that was only a half an hour. Maybe we don't really need the break, but we do have it scheduled. So why don't we take a quick break and people can spin up their machines and ask any questions. I guess we should say you should have all received an email from Melissa that has calendar files, ICS files, that would allow you to put all the office hours and these meetings on your calendar with, and I think they have the links for the office hour, the Zoom links in them. So it should be easy for you to put them on your calendar and click on them at the appropriate time. Not all instructors will be at all office hours, and we do have a tally of who's going to be available. So we know we have coverage for everything, which is good. But some instructors are more up on certain modules than others, and you may not get your question answered directly at the office hour. If the instructors that are there have not really worked on that module or not familiar with the details, doesn't mean you shouldn't come and ask, because we'll take it under advisement. And there's always the Slack channel as well. Everybody, I think, should know that we have a Slack channel. There are 138 people signed up for it. So there should be pretty good coverage there. And it's been quite active, I have to say. So we'll just wait 5 more minutes, since we do have a scheduled break, and then Gareth will start. Are there any questions while we're waiting?
Yeah, I'm gonna stick around. If you have any open startup questions, post them in chat or speak up. So I'm gonna be here, but you can all take a break for 5 minutes as Gareth is getting ready.
Okay. Is there a way to put like a note across the screen that we're taking a break, or do we have to do that through the PowerPoint slide being displayed?
It would have to be done through the PowerPoint.
Okay.
Although you might be able to share like a timer, find like a Google a timer on the.
There's no Zoom function. Somebody should recommend that.
There's the whiteboard. You could scroll it with, if you could write with your mouse.
Whiteboard, where is that? How do I get that?
Share screen option.
Oh. Well, let's practice with that. Whiteboard, there it is.
Not that easy, is it?
Well, I can't write under the best of circumstances anymore. With the mouse, it's not so good. Yeah, this is not so good. So
that's good enough.
Let's see, are there other options? Share. Oh.
What about annotate?
Is there annotate here someplace?
You can write on the screen, the regular screen.
Yeah, just open up a Word document and type it.
Oh yeah, I know that's possible if I share something like that. I was hoping that there'd be something built right into Zoom that would just allow you to paste something on the screen.
Nope.
All right. Well, while we're at it, I can try something here. See what happens if I do this. Share iPad by AirPlay. Oh, forget that. That'll screw things up. Never mind. Okay. It's 10:40.
Awesome. I'll get on with it then. Everybody see that?
Yes.
Can you see my mouse pointer?
Yes.
Excellent. Then I'll get going. So it's fallen to me to talk about where we hope to end up with all of this. We hope to end up in a position where you will be able to model geodetic data to do geophysics. I hope at least some of you that is the end goal. For the people who are more interested in glaciers, we have added material for you guys too. But I am a geophysicist who uses geodetic data to understand solid earth processes, and so that's where I'm coming from in this presentation. When we talk about geophysical modeling, what we're really meaning is some kind of idealized representation of the Earth, simplification usually, because the Earth is very complicated. But with those simplified models, we hope to gain some insights into how the solid Earth works. And here are shown some examples of geophysical models that you might want to apply geodetic data to. So for example, on the left here, we have the earthquake cycle in all of its glory, starting with coseismic deformation, which is the deformation of the Earth's surface that occurs during earthquakes. That is typically followed by a period of time in which the fault surrounding the area that had the earthquake will continue to move, a process that we call afterslip. The stresses that are generated by coseismic deformation could themselves generate deformation in other parts of the crust or even in the upper mantle. They could drive flow in the lower crust or the upper mantle, and typically that flow is some kind of viscous flow that starts at the point where the stresses are applied and then relaxes as the material that has been stressed will flow away from the source region. And on top of that, you often get also adjustment of fluids in the crust, in pores in the crust and fractures in the crust from the stresses that are added to the crust. And so the movement of those fluids can also induce deformation. We call that poroelastic deformation. So all of these things have been studied with InSAR and also can be studied with things like GNSS. In the middle here, we have a magmatic system. Very idealized. There's a magma chamber and a dike that's intrusion into the crust, and some fluids are moving from the magma chamber, which will be deflating, contracting, into the dike, which will be expanding. And again, we have theoretical models that we can use to estimate what the deformation would be from these, and use those to understand, in concert with geodetic data, what was going on. And then on the right, sort of the biggest scale deformation maybe that is studied with geodetic data is post-glacial rebound. This is the concept of loading the crust and mantle using during periods of glaciation. Large ice sheets get form and depress the lithosphere, causing flow in the uppermost mantle. In order to maintain a pressure balance underneath the ice sheet. When the ice sheet is gone, there is no longer a pressure balance. So material flows back in to restore that balance, and the Earth's surface uplifts. And by measuring sort of the zone over which this uplift is occurring and the rate at which it's uplifting, you can infer again the properties of the mantle, which is really cool. Geodetic data, of course, we're going to be talking about InSAR almost exclusively in this class, although there are other forms of geodetic data. It's just that we're not going to cover them here. So geodesy in general is the study of the Earth's shape and rotation and gravity. Here we're focusing really on the shape, and really from the sorts of processes and techniques that we are using, changes in shape of the Earth's surface. So here we have again a variety of different methods that you can use to change. You can use to measure the changes in shape. InSAR is of course the one we'll focus on. The middle panel here is actually vertical GNSS data. showing changes in vertical motion accompanying the drought in the Western United States in the 2010s. On the right is differential LiDAR, which is another really cool way that you can produce maps of deformation. And again, this is vertical deformation. And these are just a few of the methods, and we don't have time to cover all of them. And of course, this is an InSAR course, so I'm going to talk exclusively about InSAR from here on. Okay, and it would not be a presentation that I give if I did not show this slide. This has made it into pretty much every single presentation I've ever given about what InSAR is. And it's showing really the basic idea of InSAR, which is we have a satellite that's in orbit. These things are not to scale. This is orbiting around the Earth. This is the ERS satellite, the first and maybe the most influential of all SAR satellites, the first one which InSAR was demonstrated for. It orbits at an elevation of about 785 kilometers. So this is why it's not to scale. It has a wavelength of about 5.6 centimeters. And it emits these bursts of microwave radiation towards the ground as radar. It measures the backscatter from the Earth's surface back at the satellite. And it measures both the amplitude of that backscatter and also the phase. Amplitude, of course, is how bright the reflection is. That's a measure of how rough the ground is. If you've read through and looked through the phenomenology notebooks on SAR theory, hopefully that's not a surprise to you. The phase, of course, is a measure, or is a function of how far away the satellite is from the ground. But as I said, the orbiting elevation of ERS was about 785 kilometers, and the wavelength is close to 6 centimeters, so it's not practical to count every single phase cycle between the satellite and the ground. What we do instead is to compare the phase from successive passes of the satellite. So here on the right is the satellite coming back a few weeks later, after something has happened to the ground. The ground in this case has moved and subsided, perhaps in a normal faulting earthquake, as drawn here. Could also be a landslide, I suppose. Either way, now the phase is different because the ground has moved. And if you difference the phase from pass 2 to pass 1, you will get some sense of how far the ground moved in between. That is the idea. And we use some terminology to describe the types of motion that you see. If the phase increases between the two passes, we call that range increase. Means the satellite and the distance between the satellite and the ground has increased. And similarly, if the ground moves towards the satellite, the distance will decrease, and we call that range decrease. And range in general is just is sort of an oldie-worldy radar term for the distance between the radar antenna and the target. I think it has its origins in detection radar, where you have a rotating radar that's trying to detect planes in flight and what have you. The range would be the distance to the plane in flight. Here it's the distance to the ground. And we can describe the motion of the ground in terms of vectors. I should backtrack and just say one more thing. It's really important for what I'm about to say, that we only measure changes in distance in the direction that the satellite is pointing. So that range is in the line of sight direction of the satellite, which is the direction that the satellite is pointing. And of course, it's pointing at an angle towards the ground. ERS was pointing just north of east-west at an angle of 23 degrees from the vertical. So quite a steep, what we call incidence angle towards the ground. But that varies from mission to mission, and is one of the things that can give you slightly different appearing deformation for different satellites. Okay, so we can describe these quantities that we're interested in terms of vectors. The pointing vector of the satellite to the ground is shown here as the vector P for pointing. Displacement of the Earth's surface is shown as this vector U here, and you can see that the displacement of the ground need not be entirely in the direction that the satellite is pointing, because the ground can move whatever way it wants. But the pointing vector of the satellite dictates how much of that deformation resolves into deformation that the satellite can measure. as I said, P depends on things like some of these things are chosen when the mission is designed. Some of them depend on the direction the satellite is flying, or if it could be a platform that's not on a satellite, it could be airborne, in which case completely different trajectory. And also it depends on where you are within the beam of radar that intersects with the ground. The angle will change from what we call the near range, which is the closest point on the ground in the beam, to the far range. The angle generally gets shallower as you move further and further away from the satellite. And so all those things can affect what the pointing vector actually is. We typically don't use the full vector from the satellite to the ground, but the unit vector, the unit pointing vector, so a vector of the length of 1 in that direction. So p hat is how I represent that. And in terms of how you can relate range change to the pointing vector and to the 3-dimensional displacement of the surface, what you do is to take the dot product between the vector u and the vector p hat. And if you remember back to vector math from school, the dot product of 2 vectors is equal to their amplitudes multiplied together, multiplied again by the angle between those 2 things. So u, the magnitude of u, the magnitude of p hat times the cosine of the angle between them. And there's the angle between the vector u and the vector p hat, and the cosine of that angle times the length of u is going to give you this length here, because the length of p is 1. So u cos theta equals r, which is range change. So you can see in this particular case, even though the vector u is really long compared to its component in the p direction, you only actually resolve this much deformation into line of sight. That would be your range change. And so in all of the things that we do to model geodetic data using geophysical models, the real key to the whole process is having some way of modeling this vector u, given that we know from our processing what p hat will be. I also have to issue a warning at this point, because I've mentioned everything in terms of range change so far. So then in range change, it's actually a sign convention in which the ground moving down equals a positive phase change. But not everybody has historically used that convention, including me. I changed somewhere in the mid-2000s from everything moving positive phase being up to positive phase being down. My bad. It just goes to show that it is a choice, and some people will choose the opposite convention. So often, as the convention, as I mentioned, it was range change, where range increases means the ground moves away from the satellite. But if you have a ground-centric reference frame where you care more about the movement of the ground than the increase of distance, then a movement of the ground down in that convention would be negative phase change. And usually, people who are responsible about how they publish their data or how they show it will tell you that somewhere, hopefully in the captions of the figures or in the text of their papers. But that is something to be aware of, that not everybody uses that convention. And I can think of several places where you can download data, and ARIA, which we'll talk about later in the course, is definitely one of these that use the reverse conventions of what I've just mentioned. The way to check is to check if your pointing vectors are consistent with your interferograms. So in the case that I showed you, the pointing vector was from the satellite to the ground, which means an increase in distance should be in the range change direction, as I called it. If your pointing vectors point from the ground to the satellite, then you would expect everything to be reversed. If you do nothing at all to your interferogram and you process it in ISCE, with the reference image being the first image that occurred, the first image to be acquired, then doing nothing else, your interferogram will be in range change. But if you process them the other way around with the later image as the reference, then everything is reversed. And we can talk about that more in office hours if that is confusing. Okay, so into modeling then. And we can make models in various different ways. The simplest type of model, I would say, is what we would call a forward model. And that is a representation of what InSAR would see for a particular situation. So for example, here is a synthetic interferogram. This is an interferogram that is not actually data, but was produced as a model with, for example, a strike of 172 degrees, a dip of 38 degrees, a rake of minus 95 degrees. If you don't understand what these words mean, it doesn't really matter. We can specify a particular type of earthquake that happened, and we can make a synthetic interferogram that shows what we would expect to see. And sort of in a mathematical representation, what this would be a function G, which is some kind of geophysical model, incorporating the theory of elasticity for an earthquake, probably, and some other stuff, and also the geometry that InSAR is acquiring in. You would feed that function a set of model parameters, including the location of the earthquake, its depth, the geometry of the fault that it occurred on, how far that fault moved. And from that function, then you would produce simulated data, which is what is plotted here. So that's a forward model, and we can always make these. You just have to make a few assumptions about the model theory, and you have to tell it what geometry the radar would see it in. But of course, most of the time, we're interested in extracting information about things from data, not simulating data. So the other way around, for inverse modeling, you start with data that you actually observed, and you want to estimate the model parameters from it. And depending how you do this, you're essentially looking for a mapping from data to model rather than model to data. And so an example is shown here of a particularly easy to solve type of modeling problem, which is what we call a linear inverse problem. I'll talk about those again a little bit in a minute. We start with InSAR data. This is InSAR data that has been downsampled. So it's not every pixel, but sort of a selection of them. And you're trying to match this pattern with slip on a fault. Here is the attempt to match that pattern. It's a pretty good match just from eyeballing it. And there's a specific set of model parameters that will give you this particular deformation pattern. And just to show that it fits well, you can subtract the simulated modeled data from the actual data and see whether you get something that's close to zero. In this case, it's not too bad. You see, there's a lot less color variation in what we call the residual than there is from before. And so if you get a good match and a small residual, then you'll have some confidence that the set of model parameters that you estimated are actually fairly close to the real ones. That's the idea. I'll talk more about this on Wednesday, when we'll actually go through this example in a bit more detail. For studying geophysical processes such as volcanism and earthquakes, we largely assume that deformation is elastic. This has been recognized for a long time in the earthquake cycle, going back to the 1906 earthquake, and a paper that was published shortly afterwards as part of a big report on the 1906 San Francisco earthquake by Harry Fielding Reid. He was looking at triangulation data from before and after the 1906 earthquake, where he observed that there'd been a change in the angles between certain triangulation points when they were surveyed, and that if you compared the 20 years before the 1906 earthquake, the change in angle had been in one direction, and then if you compared it to the period spanning the earthquake, the angles changed in the other direction. And he recognized that this was an elastic process whereby the Earth crust had been bending in one direction due to plate motion, building up strain in the crust, and then that strain was released, and the two blocks of material that had been sheared snapped back into place, just like a pair of blocks would if you sheared them elastically. And I have a machine that I use in my intro classes that has blocks of foam that do this, and it's always great fun to use, but I don't have room for it in this room. Maybe if you come visit Riverside sometime, we can have a play with the elastic rebound machine. Anyway, we can simulate these processes using computers, so you don't have to use blocks of foam rubber, but there's some terminology involved and some things we'll have to go over in order to talk about these models in more detail. So most of the models that we use that are simple to use for modeling crustal deformation are what we call elastic half-space models. The term a half-space just refers to what we call a semi-infinite volume. That is a volume of material which extends forever in horizontal directions. So if you could, I've drawn it as a cube here, but really this cube has infinite horizontal extent. Be a perfectly horizontal horizon in all directions if you were standing on top, and it extends infinitely downwards too, but it has a free surface, so it does have a surface that you could stand on, and so that is somewhat like the Earth. The Earth is locally, laterally extensive, and the math is just easier to solve if the surface is flat. And that is why we assume that. It's not because we think the Earth is flat. We are geodesists after all, and we know what shape the Earth is. There are no flat Earth geodesists. But it makes the math easier to solve. And then within that elastic material, which is, as I say, semi-infinite, well, we would say this material usually is isotropic, which means it has equal properties in all directions, apart from, of course, the free surface, which is able to deform freely. And within that volume of material, you would have a structure. In this case, it could be a dike or a fault. There's a rectangle that's kind of embedded in this half space. You could also have different shapes depending on the thing that you're actually trying to model. And so there are models that are very, very simple. For example, this is the Mogi model, named after Mogee, who died recently, actually. Published this model in the 1950s. Mogi sources or Mogi models are often used to model magmatic systems because they involve a spherical source that can expand and contract depending on changes in pressure or changes in volume of that spherical region. And this is very, very popular for these kinds of models because it is very, very easy to evaluate. The equations are given here. That's it. You just need to know the pressure, the distance, and some geometric things, and you can calculate this. It's very simple. Obviously, it makes a number of assumptions, which may or may not be true. That the material that's in the source region is incompressible. You have to assume that the radius of the source is significantly larger than the depth of the source, otherwise the math breaks down. But as a first pass at a model, it's often not bad. I should say another thing that's bad about it, perhaps, is that oftentimes where you have a spherical magma source, like a magma chamber, you often have a volcano on top of above it. And of course, the Mogi model assumes that the Earth's surface is flat. So there's also an assumption there that may not hold, but it can get you quite close to a realistic answer. And so, given the simplicity of it, given that it's analytical, basically you just plug numbers into equations, you don't have to do any approximations numerically to solve this, it can be very it will be very rapid to run, and this is what France will take you through in the next exercise. For those of us who are more interested in faults, or if you're interested in rectangular sources that are volcanic also, or magmatic, then the Akada model is very commonly used. And this is a general solution for rectangular sources in an elastic half space. It can also do point sources. And again, this is an analytical solution. Akada famously integrated a very complicated set of equations and came up with an analytical answer that contained no mistakes. I have a Japanese colleague who said, well, you know, it wasn't that sort of it wasn't a breathtaking breakthrough in terms of understanding. It was like he didn't make any mistakes with his map. Still, not making any mistakes with your integration gets you thousands of citations, because this is a tool that many people use. Because again, it's an analytical solution, which means that all you have to do is put numbers into equations and you will get the deformation field for an earthquake, which is really cool. It's very fast to compute as a result of that. It can model shear on a rectangle. So slip, they're in the what we call the down dip direction, or in the along strike direction. That's what these arrows are showing, the potential modes of motion of this dislocation is what we call this rectangular fault. Or you can actually model opening on the structure too, or closing, which would be more appropriate for magnetic systems. So again, it's a very powerful tool that we have to come up with approximate models for the things that we are interested in modeling. The simplifying assumptions, again, may not be entirely realistic. The crust is not isotropic in terms of its elastic strength. The crust is not flat at the surface. Not every fault is a rectangle. And people have had problems actually trying to make more complicated structures out of rectangles. If you have things that are curved or elliptical, then rectangles may not be the thing that's most appropriate. So people often use this as a first pass.
Oh, sorry, I thought you were done with the slide. There is a question in the chat about the line of sight displacement. Maybe it's worth going back one more time and clarifying that. I'm not sure if you see the chat.
I see that there is chat, but I don't see what it is.
I think we'll cover this in the InSAR section. So
okay, yep, good. Yes,
that would be good to me. Good for me. We can also cover it in office hours, of course. Okay. So Akada and Mogi are examples of very simplified models that are very rapid to evaluate. At the other end of the spectrum, so the other end member case would be you could model deformation of faults or volcanic sources using finite element models, which are these very intricate and complicated models. So this is an example of an earthquake that occurred in the Himalayas. This mesh was produced by my colleague Christos Kyriakopoulos, trying to model this the 2015 Gorkha earthquake in Nepal. So what you see here, this triangulated mesh is showing the Earth's surface in the Himalayas, and you start in the Ganges plain of India down here, and then you sort of rise up into the high Himalayas in Nepal, including Mount Everest and other things. So the ground is really not flat, and that was the assumption that we were trying to test in terms of whether it makes a difference or not. Could you get away with an Akada model here, or does it actually change? Does the fact that the Earth is not flat change the modeled outcome? And it does make a difference. Actually, it changes the dip that you recover for the fault by a few degrees. So you know, there is some effect that you in some circumstances you might need to account for. In this case, it's about 8,000 meters of topography change, which is quite a lot. So you can do things like you can represent realistic topography. You can also subdivide the volume of material underground and assign different material properties to different layers. You can do all sorts of things to make your model much more complicated and more realistic. You can change the geometry of the fault to be curved, for example. Like the particular fault here probably has a change in dip as you get deeper and deeper into the crust, and further and further to the north, which on this plot is to the right. And you can incorporate not just different elastic strengths, but also different deformation modes. So as you get deeper into the crust, perhaps materials become less brittle and elastic and become more viscous and elastic. So you can give it a viscoelastic rheology, which would induce flow, which could enable flow to occur in your model over long time scales. So you have really complete carte blanche to actually design a more realistic model in all senses. But the downside of this kind of approach is that it takes hours to run these models often, rather than fractions of a second. And also that the building of the mesh, this discretized geometry volume of material, thousands and thousands, millions and millions of tetrahedra, like little pyramids tessellated together. In this case, 7 million of them. And the meshing process is itself like a real ordeal. It's really complicated. But you can learn things that you wouldn't be able to learn from other methods. So this is just showing what happens to the surface displacement of the, if you have a fault that's buried under realistic topography. And what we saw in our results, which is kind of interesting, is that depending whether you're on a ridge or in a valley, you saw a different amount of displacement for essentially a transect through the same distance from the fault. So what we think that is that the further you are from the fault surface, in this case the fault is vertically beneath you, the further you are, then the smaller the deformation that you infer from the model. So this sort of striping of our deformation pattern was actually just whether you're in a valley or on a ridge. It wasn't actually like showing that the fault was oscillating in slip or anything like that. It was just a geometrical effect. And you would not see this in a Mercator model, needless to say. There are also models that are somewhere in between the two end members of completely analytical, very fast, but perhaps unrealistic assumptions, and every effect that you ever wanted to include in a model, which might make these things incredibly complicated. There are sort of intermediate types of models. One would be what we call the boundary element models, where you, rather than modeling volumes of material like you do in finite element models, you just model surfaces. So that's a two-dimensional representation rather than a three-dimensional one. Things are much faster to model in 2D than 3, and you can still have more complicated surfaces than you do in a Mercator model. So, for example, you can model elements as model your faults as tessellated triangles. That gives you the capability of making sort of curved surfaces. It's from the manual for one of the codes that does this, showing a fault with a curve in it. You can also make potentially spherical cavities or like soccer ball shaped things made up of triangles that allow you to add more complexity to your models. They're certainly faster than finite element models. As I say, you can have complex source geometries, and the style of modeling allows you to calculate stresses as well as displacements. Also drive models by stresses. So these can tell you more things. They are slower than using something like a Carter or Mogee, quite a bit slower actually. And again, they don't allow all the full suite of things that you can do in a finite element model. You can't vary the material properties, for example. Just to say that there are multiple options for how you can model structures in the Earth. One thing that we'll talk about when we come to modeling is downsampling. Downsampling is a process of reducing the number of data points in your data set. So an interferogram can contain millions of pixels, but the displacement of two neighboring pixels will often be very, very similar. And indeed, over large areas, the displacements can be very similar. And so you don't need every single one of those pixels to represent that type of displacement. So you can just average them spatially. Of course, if you have areas where there are details, you can see in this is one of my data sets is an earthquake, that you would want more dense sampling around where there's some change going on in the data versus far away from that area. As you get to the zone where the action is, you can see these pixels get smaller. That's capturing some of the interesting information that's captured in those pixels. And we've gone from what had been millions of pixels down to a few hundred. And of course, a few hundred is much more tractable for modeling than a few million. Not least because if you try to simulate every single one of those pixels, the computation time is proportional really to the number of pixels you have. So the more things you have to evaluate, the longer it takes. You can evaluate this set of data points in a much faster time, and you don't lose much information, if any information at all, for doing that. So we will show you how to do this later on. And then there are a couple of other considerations to be aware of. This is my penultimate slide. There are different styles of inverse modeling. I've talked about different model codes, different model frameworks. But another thing to consider is the difference between what we call linear and nonlinear inverse modeling. Linear inverse modeling is really easy. It's very fast. And it requires a system of equations that you're trying to solve, the model you're trying to evaluate, to be linear. And what do I mean by that? I mean that if there is a linear relationship between a source parameter and the data, then it responds proportionately to changes. So for example, I have a fault here, which has different amounts of slip on it. Slip is just the distance that the fault moves. If you start with 1 meter of slip, you get this pattern here of displacement in line of sight. If you halve the amount of slip, you see the same pattern, but the amplitude is reduced by the same amount. You get half as much displacement of the surface. If you double the slip, you get double the level of displacement. But you see that the maximum slip, the maximum displacement is in the same place in every one of these models. So the only thing you're doing is scaling up or down the deformation pattern by scaling up or down the amount of slip. And if you have a model that's like this, then it's fantastic, because all you have to do is invert a matrix to solve for the slip. So this is a very efficient way of modeling. It becomes a least squares inversion problem, which can be evaluated in seconds. So that's great. Unfortunately, most of the things that you don't care about, that you care about for things like earthquakes, not every parameter is linear. In fact, only the slip is linear. Everything else is nonlinear, which means that if you change it a small amount, it doesn't have a predictable effect on the displacement pattern. So one example of that is the depth of your fault. So in this case, I have the same earthquake. The only thing I'm changing is the depth at which the fault is. So it starts as, I have a model at 9 kilometers, 6 kilometers, and 12 kilometers depth. And you can see that the pattern changes not just in terms of where the maximum slip is, but also in terms of how spread out it is and how much displacement you get. So looking at the locations of maximum displacement either side of the fault, at 6 kilometers, they're close to where the fault would be at the surface. At 9 kilometers, they're actually slightly further away from the fault on each side. And at 12 kilometers, even further away again. So it's not a case where you're just scaling the the amount of displacement you get, but you're also scaling you're also changing where it manifests at the surface. And so you can't use the simple linear approach to solve these problems. You could also get the same sorts of things if you change the dip of the fault, which is the angle to the horizontal. You can make it steeper or shallower, and it changes the symmetry of the deformation pattern you get, which again is not something that you can easily approximate by just scaling up or down. So in these cases, we actually have to use a much more complicated approach to solve these problems. We have to use optimization or other approaches that test a range of different values and see which one fits best. This involves a lot of forward modeling, calculating misfit, and then seeing which models have the best fit to the data, and maybe focusing on those. And the very most sophisticated methods actually will use an algorithm to do this searching for the good models. And I think our next exercise will actually go through and attempt to do some nonlinear inverse modeling. That's all I have to talk about. I see there's been lots of chatting.
There's a question about Mogi modeling and explaining the Mogi equations in the lab that we'll do next. We will go through a Mogi modeling example, and I think collectively with Gareth and myself, we hopefully will explain it to you well.
Yeah, I will say that what I showed you was Mogie's paper, so it definitely is. It definitely is the general Mogi problem.
And you'll see that Mogi seems is probably one of the simplest forward models for geophysical problems that you may have. If you look at the equation, it seems straightforward, but even the Mogi model is nonlinear. So when that comes up, we can talk about that too.
But is there a simple explanation for why Luyen's experience? Have people reformulated the Mogi equations?
Yeah, people reformulate in terms of pressure or volume, and that changes the form.
I believe there's actually an error in the original publication as well.
We have some volcano experts here. We should probably defer to them.
Yeah, so we'll look into one formulation of Mogi in the notebook that we'll run through here in a second. And we use Mogi. Mogi is conceptually and also from sort of the InSAR expression a little bit more straightforward to understand than some earthquake deformations. The reason mostly is that the deformation pattern you get from a Mogi source, which is mostly it's not entirely, but mostly an uplift subsidence phenomenon, is a bit easier to understand, and sort of the fringe patterns you get are a little bit more predictable. For earthquakes where there's strong directionality to the deformation you get, what you see in the interferogram depends, strongly on how exactly you look at the event and with what geometry you look at the event. So it's sometimes a little bit easier to get into the connection between InSAR and modeling for a Mogi exercise where the link between those two is a bit easier to understand. I don't know, Gareth, do we at any point provide links to the visible, what's that called?
Visible geology? Visible earthquakes.
So maybe later on when we are through with the Mogi, we can throw up a link in the chat. If you wanted to play with interferograms for different earthquake deformations and sort of see how the phase patterns change when the geometry of the earthquake changes. It's quite interesting and quite instructional to go through one of these modeling exercises in visible earthquake. So we can share that with you later on. Yeah, so if you don't have any more questions, we could go on with the modeling exercise. So let's see, we have another 30 minutes or so. Is that true? 35 minutes. So let's get going. And I encourage you all to switch over to the OpenSAR lab. I hope your instances are still running. Share my screen here.
It's supposed to be a break front, so 25 minutes.
No, it isn't.
No? No break?
No break. But let's see. Let's do the following.
No, I mean at 10 to 12 there should be a break, right?
Yes.
So you have 25 minutes.
Yes. So please go out to your OpenSAR lab. Hopefully you see my screen. Do you? Should be seeing my screen.
Yes.
And so, log in. If the machine is not running anymore, please log into the OpenSAR lab. And you end up in this view where you see the Geosync folder. Are most of you there? If you either give the thumbs up or give us some indication if you're ready. Okay, there's some thumbs up. Excellent. Almost ready, yes, good. So we are in section 1.2. So please click on the Geosync folder and then go into the UNAFCO 2021 folder. And then to section 1.2, Geophysical Modeling with InSAR, GNSS, Geodetic Data. So once you are there, hopefully everybody made it there. You see that there is a number of files in there, and there's one notebook. If you were listening to the introduction to notebooks, the notebooks can be identified by the little book symbol in the beginning of the, here in the beginning of the interface, and by the extension, which is IPYNB, which stands for IPython Notebook. So please open this notebook that's called UNAFCO InSAR Geophysical Modeling Homework 2. So this should all have started for you. Hopefully everybody sees the notebook interface, and you can follow along as I talk you through the exercise, and we go step by step through this notebook to execute the code cells. So this notebook now provides you an example for volcano source modeling using InSAR data, and specifically we'll look at a volcano, as you see here in a second, in Alaska, the so-called Okmok volcano in Alaska. And we will use a Mogi source model to try to describe the physics behind the deformation we see, and basically use forward models and a brute force inverse modeling approach to find the best fitting source parameters for this inflation event. So please go through these first few code cells. The way you do it is you highlight a code cell and you either click run. Alternatively, you can highlight a code cell and do Shift Enter as a keyboard shortcut. This is something that I like to do. And so please go through these first few code cells until you are reaching section 0. These first couple of code cells just make sure that your notebook is running in the right kernel, in the right environment. It should say here in the top right corner, you should say that you're running in the UNAFCO kernel. And if that's the case, then these two code cells should not throw up any error messages. There's a note, there's a homework assignment in this section. So section 5 is a short homework assignment that I'll ask you to complete. And once you're done, you should submit a PDF version of your completed notebook. And you can do this by right-clicking on the browser and then click on print using basically your browser printing functionality. Okay. So hopefully everybody is at this point. The way these notebooks are built are always similar. In the first sections, we always have to import the relevant software packages that we use in this notebook. In this case, we mostly use two Python packages. We use NumPy, which is a package for scientific applications of Python and allow you to do processing and do analytics on multi-dimensional arrays. And we also use a package called Matplotlib, which is a library for creating graphs and diagrams that look similar to what you would see in MATLAB if you assuming that you are experienced or know something about MATLAB. Oh, yeah, there's a comment that some people cannot collapse sections. Don't worry about that. I have activated an extension that's called collapsible headings. If you didn't activate that extension, then these sections will look uncollapsed, but that's fine. There is, if you're interested in activating this in the video, in the pre-course video, there's a section that talks about these notebook extensions, and it will explain to you how you can activate collapsible headings. Okay, so please exercise this code cell, again, by clicking run or by clicking shift enter. And you'll see that it will import Matplotlib and NumPy. And so once the code cell is executed, you see there's a little number here. This is your third code cell to execute, so you should see the number 3 next to your code cell. Make sure that you exercise all code cells in order. Okay, so in section 1, you see there's a little bit of information on the event. What we are looking at here in this case is a single pair of C-band ERS2 images. One image was acquired in August 18, 2000, and the second image was acquired on July 19, 2002. So it's an interferogram that has a 2-year time span. You see, you'll see that even though this is a 2-year interferogram, the coherence is good in this interferogram, and the coherence is fairly high because this area is not very vegetated, and we are using a pair here that is 2 images that are acquired at about the same time of the year. So one is acquired on August 18, and the other one is acquired on July 19th. So it's reasonably seasonally coordinated, so that whatever vegetation is there is at about the same growth state, and whatever snow or ice features may be there are also at about the same state. You'll see that this interferogram shows an inflation of Okmok. Okmok is a volcano in the Aleutian chain, so this little map inset shows you roughly where Okmok is located. It's a very nice volcano in the sense of InSAR. It tends to deform quite a bit as magma is moving around under the volcano. And so in this case, there was some magma that was injected into the source under the volcano, leading to an inflation. This figure here shows you also that GPS confirmed that there was inflation throughout this time, that sort of had a deformation that was sort of up in the center. So there's mostly uplift in the center, as you can see here in this rightmost inset, and there was a little bit of an outward motion also. And if you combine those two visually, it already almost looks like you have a ball-like inflation, like if you inflate a balloon where the surface moves up and slightly outward as the inflation happens. So the primary problem that we're trying to do is we try to use our observations to figure out how much magma was injected into the volcano, how deep the source was, and then what location the source was located. So if we next go through section 2, there we are downloading and visualizing the InSAR datasets. So in section 2.1, we first download the data. In this case, the dataset is pre-processed and available for you in an Amazon S3 bucket. So the code cells we go through, and you can click through one by one, is first it creates a subfolder into which all of our data sets and all of our plots will be saved, and then it grabs our data set from an Amazon S3 storage device and pulls them into your machine. So it downloads the data set, which in this case you see here is an ERS data set with 2 dates from the August 18th of 2000 to July 19th of 2002. And the .unw it's an unwrapped interferometric file, which at this point may not mean a ton to you, but this is absolute deformation results for this volcano. In the next code cells, we set some variables. We tell the program how many lines and samples our data set has. So the data set has about 11,000 samples and about 1,000 lines. And the posting is 40 meters, which gives you an idea of how much area is roughly covered by this interferogram. We also define the sensor, sort of how much deformation, how much one phase cycle, how much deformation one phase cycle corresponds to. You will learn later in these lectures that it takes about half a wavelength of deformation to go through one entire phase cycle of interferometric phase. So in this case, we have an ERS C-band satellite, which has 5.6 meter wavelength, 5.6 centimeters wavelength. So half the wavelength is about 2.8 centimeters, or 28 millimeters in this case. So now we read also some additional variables. We read a file that's called the coherence, also a variable you will learn about a bit more later in the lecture. It basically is a layer that describes the quality of the phase in numbers between 0 and 1, with 0 coherence corresponding to pixels where the phase quality is very poor, and a coherence very close to 1 would indicate that the phase quality is very high. We are using the coherence to sort of mask out some pixels where we don't trust the phase values a great deal. The next code cell takes our phase measurement and converts it into a line of sight displacement measurement in the unit of millimeters in this case. And then at the very last code cell, we mask out some pixels where the coherence is low. Okay. So now that we have done all of this, we can visualize the interferogram. So if you go through the code cells in section 2.2, we calculate some variables. We create a subfolder that's called plots. And in that folder, we'll deposit some JPEGs that you can later look at if you want to. Then there's a little plotting function that's being written. If you're familiar with Python, you will recognize that we are defining a function here. We call that function plot model, and it takes our an input file with its line sample extent and its posting in meters, and creates a figure for that particular data set that we are plotting. And so then the last code cell down here uses that plot model function to create a figure of the interferogram or the deformation information that we have in this particular case. So there's some questions I see. I cannot collapse sections. Okay, pixels with low coherence get removed before phase unwrapping or after phase unwrapping. In this case, this is done after phase unwrapping. Thanks, Gareth. So what you see here is the deformation map that was observed by ERS for this event. You see here blue colors. In this case, blue colors mean that the distance to the satellite reduced. So the areas that are indicated as blue, they moved closer to the sensor, which means in this case that that's predominantly an uplift signal, where the point on ground uplifted and moved a little bit closer to our sensor in space. On the right-hand side, you see the absolute deformation, the unwrapped, basically deformation signal. Green means, in this case, that the deformation is 0. Blue means we are moved toward the sensor with about 30 to 40 millimeters, so about 3 to 4 centimeters. On the right-hand side, you see the same information, but now rewrapped into an interferogram. So an interferogram originally only measures deformation between 0 and 2 pi. And in this case, if we go from 0 deformation to the center, we go through a little bit more than one full phase cycle of deformation. There's a question. It uses 2D phase unwrapping. Would it be better to remove pixels before phase unwrapping? Yes, we're using 2D phase unwrapping. I'm not sure if you have a section that talks about phase unwrapping. Paul, do you recall? Does anybody talk?
Not in detail, no.
Yeah. So the modern phase unwrapping methods, they use methods that are called branch cut methods, where the spread of phase unwrapping errors that may occur is limited. So in many cases, unwrapping across decorrelated areas doesn't cause a huge amount of trouble. The main issue of not masking before phase unwrapping is mostly time. If you have a lot of uncorrelated pixels, like all the ones that are out here in the ocean, resolving all of the phase unwrapping problems takes a longer time. It sometimes would make sense to mask them out first. It would make phase unwrapping converge much faster if you do that. Okay, so this is the data we have. So we have an uplift signal, which indicates that most likely there was magma shooting into some source under the volcano, causing uplift of the volcano. So maybe a quick question here. If you see my mouse pointer here, given the deformation signal, where do you think was the source was located? Was it located somewhere over here? Maybe that's position 1, maybe closer to somewhere over here, where my mouse pointer is now as position 2, or maybe closer to where my mouse is located now in position 3. What do you think is most likely? 1, 2, 3. So there's lots of 2s. So intuitively, you already understand what it means to do inverse modeling. Is we try to find out the model parameters that fit the data the best. And very likely the XY location of the source is close to where we see most of the deformation in the interferogram. So we'll get to that in a little bit, a bit more. Okay.
Sorry, I have a short question.
Yes, please.
If you go up a bit about the figures, in the middle part, we can see that there is no information what kind of deformation. So yeah. we are estimating based on our deformation that what is the highest deformation point.
So in the end, what we do is we take a model to calculate predicted deformation. We'll look at that in a second. And then we find the model parameters where the predicted deformation matches the true deformation or the measured deformation, the observed deformation the best. We are not necessarily only looking for the point with highest deformation. We look at the entire shape of the deformation pattern.
Okay, thank you.
Okay. So now a few words about the Mogi model. So if you're, by the way, so we see here that in these markdown cells, you can show equations. I'm not sure if you see funky stuff like I do here. Sometimes the equations don't render perfectly, especially if you present online. If yours looks strange, you can double click into that code cell. And this actually exposes a bit the text behind this markdown cell where you see, LaTeX equation formatting here. And then once you double click it, you can execute this code cell again, and it fixes the formatting. So this mostly happens if you present and you are zoomed in to your browser. It sometimes looks a little funny. So here's the Mogi forward model. And so what the Mogi forward model describes, it describes a three-dimensional ground displacement that's called U that you may observe due to an inflating source, a point source that's located at this coordinate, the coordinate x sub s, y sub s, and z sub s. And we assume that this source location, or the source down there, inflated because there was a certain amount of magma volume that entered this point source. And this magma volume change here is indicated by V in this particular notation. And you see that here that the deformation, the three-dimensional deformation, then depends on a few parameters. It depends on how much volume we inject. So the more volume we inject, the more deformation we get. And it depends on the relative location of a pixel X in the scene relative to the source location. So X minus XS, the difference between the Y location and the Y source location, and the Z location and the Z source location. In our case, in the interferogram, we assume that Z is 0. So we assume mostly that the deformation is measured in a flat plane with a Z value of 0. And so this here shows the depth of the source relative to that 0 plane. And what it also shows is that the amount of deformation you get changes with the radial distance from the source. So the further away we are from the source, the less deformation we get also. Another variable that plays a role is the Pulsar ratio that's indicated with this new variable. And this describes how a certain country rock reacts when put under stress. So it basically tells you how pressure at depth is being propagated forward to the surface. So this means that depending on what soil properties you have in a certain location, you may want to adjust this Pulsar ratio a bit, and the way pressure on the surface is then propagating to under the surface is propagating to the surface may be slightly different. In our case, and in most cases when you run a Mogi model, you assume that this new variable is fixed, and you also assume that the properties of the soil are constant all the way between the source at depth and a measurement point on the surface, which is one of the limitations of the Mogi model, which makes fairly bold assumptions about the homogeneity of the soil and the country rock between the source and the surface. So as you see, what the model predicts is deformation in 3 coordinate directions, X, Y, and Z. But InSAR, as Gareth explained earlier, only measures deformation in the so-called SAR line of sight. So in our forward model, we have to account for the fact that we're only seeing the line of sight. And so what we are doing is we project a true 3-dimensional deformation that's indicated here with this vector. So our 3-dimensional deformation U is being projected onto the line of sight that's indicated here by this vector. And so what we are seeing of our deformation U is only this component alpha. Does that make sense? So that's the piece that we see of a 3-dimensional deformation on the graph. And so the mathematics behind this projection is shown down here. We perform an orthogonal projection of our vector U onto our line of sight to get the InSAR observed deformation D. Okay. Hopefully so far this makes sense. And so with these 2 components, we can now define a forward model. So we can calculate a Mogi predicted surface deformation based on a set of Mogee parameters, and the Mogee parameters are north, northing, easting, and depth. Here, these are the XYZ parameters, as well as the volume change that may have occurred at depth. And so this function calculates the final surface displacement by first evaluating this equation up here, the Mogee equation, and then projecting the Mogee equation into the line of sight. So the first code cell, please, that you run here calculates the Mogee forward model. And then the second code cell takes the output of the Mogee forward model and calculates an InSAR displacement from it. Okay, so now we have the function set up, and now we can play with that forward model function. So in section 3.4, if you run this code cell, we are now creating forward model plots or calculating predicted surface deformations, and we do that by presupposing a source model depth, which in this case is given in kilometers. So the source model depth is given as 2.58 kilometers under the surface. We are presupposing a volume change, which is given in cubic kilometers, so 0.0034 cubic kilometers as volume change. And in this case, we are experimenting with different X and Y locations. So we move the source around a little bit to a grid of 9 different XY location combinations. And if you look at the output, you will see you see a little bit of a star. The star indicates the XY location of the source. And you can see when the star moves around, when we move the source to slightly different locations, the predicted surface deformation follows. So this should give you a little bit of an idea of how the forward model works. You may see also that if you look at the deformation here, that the star is not quite in the middle of that uplift blob. You see that? That is a little bit asymmetric. It's not quite in the center of the blob. The reason for why it's not in the center, it has to do with our image geometry, which is a side-looking geometry. So we look at the ground in a side-looking geometry, which causes a little bit of an offset between the actual true location of the source and the deformation pattern it causes, the InSAR deformation pattern it causes. Okay, there's for later when you go through this notebook again, and when you do the homework, there's a suggested exercise in here where you can start playing around with these source model parameters by modifying some of these variables that are set in this code cell. So you don't have to execute that code cell now, but there's a section where it says change variables here. And you can play around with the source depth, and you can play around with the volume change and sort of get a little bit of a feeling how the deformation changes when different parameters of the source model are changing. It's a quite fun exercise to go through. Okay, so the forward model gets us halfway there. It basically sets up the physics that connect the observation in the interferogram with the parameters of the Mogee parameters of our source. But it doesn't yet allow us to actually calculate these interferograms. The calculation of these interferograms is done by solving the inverse model. And Gareth had sort of a little more of the theory behind the inverse modeling in his slide deck. But the inverse problem, in essence, tries to find the best source parameters, X, Y, Z, and volume, of our Mogee model by minimizing the misfit between the predicted deformation by running a Mogee forward model and the actual observed deformation that we get from InSAR. So what we are trying to do is we basically, in the simplest case, try out different combinations of these 4 parameters until we find a set that gives us the smallest difference between the forecasted deformation and the actual measured deformation. And the key is, in order to find the best fitting source, we have to sort of determine of how we define smallest misfit. And the way we usually do this in most cases is by using the so-called methods of least squares. And the method of least squares is encoded in this little equation up here. Basically, is what we do is we calculate pixel by pixel the difference between the forward modeled deformation and the observed deformation. So we do a pixel by pixel difference. We then square pixel by pixel the result of that difference. And then once we square the result, we sum up all of these results of the squaring, of the differencing and squaring for all the different pixels. And we get a number. And if the model and the deformation have very little in common, this number is going to be very large because the difference on a pixel by pixel basis is going to be large. If we square it, the difference is getting even larger. And if we sum up all of these squared differences, we get a very, very large number. And the idea is that there should be a set of model parameters that minimize this squared difference, the sum of the squared difference between model and observations. And the way we will do this is, first, let me experiment. Let me show this to you here real quick. In 4.1, if you run this code cell, what we do is we calculate part of that misfit function. And so in this case, what I will show you is the difference between the model and the observations. We don't actually go through the squaring and the summing, but we calculate the difference between those two. And we do that here for these 9 cases that I showed you earlier. So you see here for all of these 9 little source model locations that you see again indicated by the star. For those, we calculate the forward model, and then we subtract the observations from the forward model. And this is what we get. So in some of these cases, you see that there are large misfits left in many of the pixels. There are some places where the misfit is negative. In other places, the misfit is positive. You get sort of these little dipole signatures in a lot of places. But it turns out that there's one solution, which is the solution closest to the center, where it seems like the model prediction and the observations are fairly close. You see here that most of the pixels in this case have a greenish color, meaning that the difference between observations and models are very small. And you could imagine that the misfit calculated as the sum of the squared differences will be smallest for this case out of all of the 9 cases. Is that clear? So it shows that this is not a bad solution for the model parameters. So we could now, of course, go through this like one by one. I could like let you rerun a certain code cell one by one. We do a brute force finding of the minimum, the best fitting source parameters using sort of a brute force approach. And what we do in our case is we run a grid search where we find the best fitting model parameters X and Y. So the sort of latitude and longitude best fitting location for the source model by basically trying out different options. So we go through a certain grid, an XY grid, small steps in an XY grid to find the XY solution that provides the smallest difference between the model and the observations. In this case, we assume that we know the depth of the source, and we assume that we know the volume change. And say maybe we have information from other data, maybe from thermal data sets. We may know something about the expulsed volume, and maybe from some seismic data, we may have an idea of the depth of the source. So we assume that we know those two, and the only thing we estimate is the best fitting X and Y location. So if you run this code cell, what it will do is it will go through a total of 176 different experiments, where it basically tries out different combinations of X and Y. For each of these experiments, it's calculating the misfit. So it's calculating the sum of the squared differences between observations and measurements. And then once it's done, it looks through all of the misfit results and it picks the combination of X and Y that gave us the smallest misfit. There's some questions. In all cases, even the center case, there are positive misfits, okay, and there's some negative misfits. We'll get to causes of misfit here in a second. Okay, so by running through the experiment, it found out that we have an X coordinate of 2.6 kilometers, 20.6 kilometers, and a Y coordinate of 21.8 kilometers as the best fit between the source, the forward model and the observation. So that's our best estimate for the XY location of the Mogee source. To verify if it's a good fit, in 4.3, we can now plot the misfit function, which is shown here. So what this plot here shows is every grid point in this plot is one of a set of XY combinations that we tried out. And in color coded, we see the misfit we found for this XY location. So here, for instance, for a northern coordinate of 23 kilometers and an eastern coordinate of 19 kilometers, we got a fairly large misfit in the order of 3 times 10 to the power of 7. You see that the misfit sort of seems to continuously decrease the closer we get to the center of this misfit function. And at the location where the star is plotted, that is our location where the misfit was the smallest. So you see we found the misfit at about 21.6 kilometers in northern and 21.6 kilometers in eastern. You see also quite nicely, we in this case, we used step sizes in X and Y that were the same. And we see that we get a misfit function that is almost circular. What this means is that there's only a single combination of X and Y that fits this data set the best. And it doesn't matter which direction I walk away in X and Y direction, the gradient at which the solution gets worse is about the same. This is a good indication. If you see a misfit plot that is about circular, it is a good indication that there is no correlation between the X coordinate and the Y coordinate, or between the two variables that you tested in this case. There's no correlation between the eastern and northern coordinate of the Mogee model. Okay, so we see we found clearly a best solution. The misfit function is very nicely behaved. It sort of gets smaller and smaller and reaches a global minimum at some point. Oh yeah, so these coordinate axes here are in kilometers. We can also verify that it is a good solution by, again, comparing the observed and predicted displacement maps. So in this section 4.4.1, we are plotting first the best fitting, we plot first the observations, then we plot the best fitting forward model. And if you compare those, top to bottom, you see that they're very similar to each other. And then we also plot, the forward model without the mask. So if you wouldn't lose any pixels, if every pixel would be fully coherent, this is what the forward model would look like. And so we're losing some pixels because some pixels were not useful or couldn't be used in the analysis because the phase quality was too low. So in addition to this, we can also plot the difference or the misfit between models and observations. And if we do that, we get a plot like this, where you see that after we subtract the best fitting model, the residual signal is quite small. So in many places, the color that we get here is now green, meaning that the misfit is very close to 0. We have some locations where we see some blue misfit and some locations where there's some red misfit. And maybe before we end, we're already a little late. Maybe somebody has any ideas of why the misfit is not 0. What could be reasons why the misfit is not 0? Any ideas?
Nonlinear displacements.
There could be nonlinear displacements. So in some ways, the Mogi source is a nonlinear source, but I guess you're getting to maybe weaknesses of the model. So there's some suggestions. The model is not perfect. We talked about that the Mogi model is a simplification of the truth in many ways. We talked about this Pulsar ratio, which describes the properties of the soil. And we talked about us assuming that the soil properties are all the same spatially. That is that's one limitation of the model and one cause of misfit. There are some suggestions about atmospheric errors, correct. This is something that will come up in the next few slides. There's a little bit of a figure down here. Even though radar can penetrate through clouds, that's always sort of why we like it so much, is we can provide 24/7 observations. The atmosphere does have an impact on how quickly the signal penetrates through the atmosphere and reaches the ground. And sort of atmospheric properties can vary a little bit in space, and that can cause some phase variations, non-zero phase variations that you can also see in this interferogram. Somebody said like the DEM may be incorrect. That's also correct. You will hear about that we are correcting for the DEM when we calculate deformation maps. So that's going to come up, I think, in one of Paul Rosen's lectures. And so that's another source of errors. There's a variety of errors that you've mentioned already, and noise in the data is another one. Tropospheric effects is another one. That's all correct. Here also, the reason why we masked out this thing in the middle, you see that there's a hole right in the middle of the area. This is actually not because of decorrelation. The cause here is that in this crater of Okmok, there is a lava flow, a fairly recent lava flow from 1996. And this lava flow is still cooling. And when the lava that's being emplaced is cooling, it shrinks. The lava flow over time is slowly shrinking. And we actually get slight deformation signals in this area that is being masked out. And I think what we did here is we didn't mask out quite enough, so you get some residual shrinking signal from this lava flow here in this one corner. Oh, I think it's the blue signal over here that's residual of the lava flow. Anyway, so you have good ideas of what may cause residuals, and basically what other signals are in the InSAR data and what limitations you already have of models. And we'll talk about these other signals in interferometric data a little bit more as we go through this course. So hopefully this gives you a little bit of an idea of the concept of forward modeling. Now, before I let you go, in this notebook, in section 5, there's a little homework exercise for you to go through. Let me format this correctly. And so previously, a few code cells up, we did a grid search where we assumed that we know the depth of the source and we know the volume change caused by the source, but we didn't know the XY locations. And we went through a grid search to find the best XY location of the Mogi source. So what I want you to do in the homework is to basically take this code cell. So this is a copy of the previous code cell, and modify this grid search such that instead of searching over the XY space, which you do here with these first two code lines, I want you to search through the Z and volume change space. And instead of keeping X and V as known parameters, I want you to take the previously estimated X and Y coordinates, keep those fixed, and search over the Z and V space. And basically find the best fitting source depth and the best fitting source volume. And so in order to do this, you have to take this code cell and make some slight modifications to this code cell and see if you can figure this out. You should then come up with a best estimate for source depth and volume. And in order to hand in the homework, please modify this code cell, fill in information into these markdown cells below. And once you are done, save the fully executed notebook by right-clicking and printing the fully executed notebook. So there's some questions like for some of you, this may be easy because you have experience in Python. For other ones, this may not be as easy. So feel free to get help, coordinate via Slack, and sort of work your way through this in teams if need be. The goal is for all of you to go through this process once, and the ones that are already knowing the Python, they can probably observe a little bit of the physics. So some of you may be stronger in the physical background, other ones may be stronger in the programming background. And by communicating with each other, hopefully all of you learn some slices of this exercise as you go through. Great. This is what I wanted to show you today with a little bit of an outlook of the homework. Do we have any more questions?
Okay.
I went long.
Thanks, Franz. We probably should move on. If you could stop sharing, I'm just going to put up a break sign. We need a break now before we start the next segment. So because we're a little bit behind, we'll shorten the break by a few minutes. So we'll go to 12:20 in California. So that's about 7 minutes from now. And then we'll start the InSAR segment. So we'll talk to you soon. Let's get going. As you can tell from the fact that we're a little bit behind already, it's really hard to convey the information we're trying to convey in a short amount of time. So that is also true for SAR and InSAR, which is why we put the SAR module in the pre-course. And it is also true for InSAR, which normally we have much more material in here for a in-person full-day course. So what we're going to do today is try to go quickly through this notebook. Since the notebook has narrative in it and figures and exercises and quizzes, it's something that you can go through yourself pretty much without instruction. But I will try to go through it in enough detail so that you can guide yourself through it if we don't have enough time to cover everything. I'd like to try to finish up today close to 2 o'clock. I have to leave at 2 in California. So let's see how quickly we can get through this without confusing you. And of course, continue the questions in the chat and we'll slow down as necessary. So first, before I get started with this, I just want to say we're talking mostly about the geometric aspects of SAR in this particular notebook. We'll talk more about the phenomenology in the next notebook on correlation. about a half an hour per each, and I'll try to speed that up a little bit. But I'm hoping, as we had mentioned in the pre-course, that you've gone through the SAR notebook that was in the pre-course material, so that you're familiar with terms like backscatter and range and azimuth, layover, shadow, speckle, resolution. Those kinds of things are kind of used here without too much explanation. So hopefully you've done that. And if not, you can always go back to that and then come back to look at the recording of this. So let's talk about interferometry. We are looking at the phase, as Gareth explained. We're just going to go through a little bit more detail of what that phase means here relative to what Gareth was showing there. So basically, we're using the phase of an electromagnetic wave that's propagating in space from the spacecraft down to the ground, bouncing off the ground and coming back to try to estimate what that range is from the spacecraft to the surface and how it's changing over time. So according to the wave equation, you get a phase from a plane wave, basically a sinusoidal wave that's propagating in space, that is proportional to 2 pi times the range distance itself divided by the number of wavelengths. So basically the phase is measuring in radians the number of wavelengths between where you are and where you're going to. And that's represented in this figure here, where you can see that we have 2 plus some number of wavelengths represented in this distance here. And that comes back as a radian phase. So as Gareth mentioned, and as you'll see in the correlation notebook that's coming up, we cannot really measure the absolute phase easily. There's millions of cycles, and the ground itself imparts its own phase on the surface. So what we can do, though, assuming the surface doesn't change too much, is we can measure the difference in phase from one time to the next, or from one position to the next. Because phase is usually measured down to degree level accuracy, this means that given the wavelengths that we're looking at, 360 degrees of phase is one wavelength, we're talking about being able to measure range changes down to millimeter kinds of accuracy. All right, so that's the phase, but we're looking at interference. And as I said, we have to do this differentially in order to be able to measure this range difference. So here's the typical example of Young's double slit experiment, where we have a light source creating 2 coherently connected new light sources through these slits in a otherwise opaque surface. These waves then propagate, and on a surface where we're actually imaging, we can measure the interference pattern where they constructively interfere and destructively interfere, and get basically a fringe pattern here. If we could measure this using phase, then we would see the phase changing from minus pi to pi and over this plate. Is somebody going to say something? I hear a microphone. So this interference pattern is manifest in a SAR system, as you see depicted here. One slit would be one SAR antenna, the other slit would be another SAR antenna. So we're emanating a radar wave. It propagates through all space. Because of the distances involved, by the time it hits the ground, it's effectively a plane wave, but we depict it here with the actual curved surfaces. And these 2 waves intersect the surface with different phases, as you can see here. So we're looking at, in this particular case, at the same time, 2 different observations from different vantage points give you a phase difference, which would be proportional to the topography. And that's sort of the way this kind of started out, looking at topographic phase from aircraft systems with two antennas mounted to it. So here's an example, just an example of what we're doing here. So here's a standard image that you've seen, and if you looked at the SAR notebook, you would have seen this described in more detail. You can see the brightness, which is the backscatter level, and some of that is the actual natural backscatter of the surface. Some of it is the topographic relief affecting the brightness by tilting the slope up towards the radar or away from the radar. But so it gives you some hint of topography, but it doesn't actually measure the topography directly. But if we form the interferogram, which is given by this equation here, which would be familiar, the S, and would be familiar from the SAR notebook, then the S is comprised of an amplitude and a phase. So S1 is one image, S2 is another image. And if we take the conjugate of the second image, multiply it by the first one on a pixel by pixel basis, then we get the two amplitudes and the difference of these two phases. So here's how we form that phase difference that we mentioned earlier to do the interferometry we're interested in. And you can see then the interferogram, as it's called over here, depicted as phase slightly modulated by its amplitude, indeed shows fringes, color changes going from 0 to 2 pi or minus pi to pi that sort of mimic the topographic contours of this surface. So that's the first order aspect of interferometry that we exploit to do topography, the SRTM mission, and now TandemX, which created the Copernicus DEM. Those were both based on this principle of interferometric mapping. We'll say a little bit more about it as we go down here. So here in equations is the explanation of the interferometric triangle. So we have our two observations, phi1 and phi2, from the two different vantage points. That gives us 2 pi over lambda times range for one, 2 pi over lambda times the other range for the other one. And so if you take the difference, you get this differential range, delta rho. This factor of P we'll describe in a minute on the next slide. So don't worry about that now. It's either 1 or 2. So this is our differential phase measurement, and you can see it's directly proportional to the difference in the range between the two. So if we happen to know in our interferometric triangle, the baseline here and the intrinsic range, and we measure this phase difference, we can then use basically the law of sines in order to invert using this differential range estimated from the differential phase, this equation to get the angle, the precise angle at which this range was measured. And from that precise angle, knowing the height of our SAR antenna and the range, we can estimate the topographic height. So this is the basic set of equations in 2 dimensions for measuring topographic height from an interferogram. This factor of P is important depending on how you do the imaging mode. So if you are in a situation which we'll call the classic or single pass interferometry method, then you're transmitting from one antenna and you're receiving at both antennas. And that, in that case, you can go through the equations and show that the differential phase is basically 2 pi over lambda times this difference in range. Whereas if you do this, what we call ping pong or repeat pass mode, where you're transmitting and receiving off of one and then transmitting or receiving off of the other, which is possible for a system like SRTM if you wanted to do that, then you get an extra factor of 2 just by going through these equations here. So then that differential phase is 2 pi times a factor of 2 over lambda delta rho. So this is 4 pi over lambda. So in all the equations you see for repeat pass systems, you generally have a factor of 2 in there because of the fact that you can't usually transmit at the same time. So here, by the way, these quizzes hopefully work for everybody. You have to execute the notebook from the top, and there's a widget that gets calculated at the top. So if you just hit cells run all when you enter the notebook, it will run all the cells, and then it will set up all of these quizzes for you. And then you can start clicking on buttons and checking whether you get the answer right or not. Okay, so normally at this point, we go through a big discussion of how you derive this equation, but in the interest of time, you can show very easily from the simple equations that you just saw up above that you can approximate the interferometric phase for this topographic situation in terms of that baseline separation, the baseline vector and the look vector that you have here. And that's expressed in this form. And what that basically is saying is that you take the baseline vector and you take the dot product or project it onto the look direction. And what that is basically saying is that as long as the baseline here is small relative to the distance from the SAR system down to the surface, you can think of this look vector here and the look vector going from this point of the second antenna down to the surface as being essentially parallel up in space. And if this baseline is only 100 meters and the distance is 1,000,000 meters, then that's a reasonably good approximation. So this is basically the so-called parallel ray approximation to calculating the interferometric phase from the baseline. And this is helpful to know. And you can sort of derive a lot of intuition from it. So we refer to the interferometric phase then in this situation as being the parallel component of the baseline, parallel, that is, to the look direction. And here's another expression that is typically used for deriving further equations that you'll see down below. I don't know, are there any questions so far? This is pretty basic stuff, just a few equations to describe the interferometric phase in terms of the look vector, which is changing with topography, by the way, and the baseline, which should be effectively fixed in space. Okay.
There's just a couple of questions that came in. What should be the threshold value for perpendicular baseline for earthquake deformation analysis is one of those.
Yeah, so the threshold value of a particular baseline, it's not so much for earthquake deformation as it is for just robust interferometry in general. And we're going to talk about that in the second part of this for the during the correlation study. So we'll get to that.
And a second one is the zero baseline assumption valid if the images are taken from an aircraft?
Okay, so zero baseline or the parallel ray approximation. I'm not entirely sure what that means. So in general, zero baseline. So I need more information to answer that question. I'm not quite sure what that means.
Yeah, we will do this in chat.
Yeah, okay. We can't find the Jupyter Notebook. I meant to start with that. Yeah, so the Jupyter Notebook, you go to UNAVCO 2021, and it's done in here under the InSAR theory. I'm not going to click on it because that will just bring me back to here and create a new window. Okay, so a little bit more explanation on that zero baseline assumption question would be helpful in the chat. Let me just keep going here so we don't lose too much time. Okay, so we can calculate from this equation that we had on the previous page for the phase, what the phase gradient is. The phase gradient is relevant because it tells you how the fringes are going to change, how the interferometric phase is going to change in your image, and give you some intuition about the quality of the signal. So we can just take the gradient, which is defined as d by ds, which is the along track dimension, and d by d rho, applied to the differential phase, and that's given here. And since b is a fixed constant to first order, the derivative is applied to the look vector. So, and as I said, the look vector is changing with topography, so this will be not a constant. So you can go through the equations, which we typically do in a longer course, and derive these expressions. So the derivative with respect to range is given by this expression here, which you see has this term B perpendicular. B perpendicular is the component of the baseline that is perpendicular to the look vector. So that's expressed as B cosine theta minus alpha, theta being the look vector, look angle, sorry. and alpha being the baseline angle, which I think you see up here, so up someplace. Anyway, B is defined as B cosine alpha, B sine alpha. The look vector is sine theta minus cosine theta. So alpha is actually the angle from the horizontal here up to the baseline vector. Maybe that's not defined anywhere. Okay, so you can see that the fringe rate, shall we say, the change of the differential phase as a function of range is going to be a function of the baseline length, the baseline, the perpendicular component of the baseline. So if that perpendicular component is 0, then you will have no fringe rate variability. So if you actually fly back to the same point on your orbit and you see something from the exact same point of view, or you don't have a separation between the two, then you're going to get no fringe variability. And you can also see that even if there is no slope on the surface, you're just on a flat surface, that you will get a fringe rate across your image. So that's just due to the fact that the geometry of the look vector is changing as you go from the near range of your image to the far range of your image. You also get a fringe variability in the along track dimension too, given by this expression. In this case, if there's no slope, you don't have any particular fringe variability in the along track dimension. But if there is a slope in that direction, then you do get fringe rate. And that makes sense. All right, so typically you'll see in interferometric workflows, you're going to see that there is a process to take that natural variability of the fringes that is not really related to the topography per se, but just related to your viewing geometry, and remove that or flatten the phase. And what you saw up above when I first introduced the interferogram was such a flattened phase interferogram. And you do that by essentially knowing your flat surface, taking a reference surface, which could be the geoid or the ellipsoid, and calculating what the fringe rate should be for that reference surface and subtracting that from the actual surface that you have. So the flattened interferogram would be expressed basically in this fashion, which is the difference between the actual angle and the reference angle. The geometry for that, the calculation for this reduction is given here, and it shows that the flattened fringe rate is proportional to the perpendicular baseline as it was before, and this differential angle going from the reference surface up to the actual surface. That's this d theta here. And that d theta is just proportional to the height of the target above the reference surface. So that shows then that this differential phase, after you go through this reduction, is proportional to the baseline, and it's proportional to the height of the surface. So again, if the baseline is 0, for whatever reason, then you have no sensitivity to topography, no fringes. If the baseline is large, then you have greater sensitivity to the height changes in the phase. All right. There's something called the ambiguity height, which can be calculated from this expression here. I'm not going to go over that, but you can test your understanding of that ambiguity height as you go through this yourself for homework. All right, so that's the interferometric triangle for mapping topography, but the reason you're here is not for topography per se, it is for understanding differential phase as though you have in the situation where you have no baseline and something on the ground has changed. So the range is changing, but not because of triangulation per se, but because there is a change in the range of the scatterer itself. So again, we have, in this case, 2 different times. And so we have a range at time 1, a range at time 2, and we're taking the difference between those ranges through the phase difference to try to get at what the displacement of the surface is as a function of position. And here's just an example from an earthquake showing the signature of that, which is not topography per se. It's the change in the position of the surface and the line of sight direction from one time to the next. And again, this is the projection onto the look vector. So you're just measuring one component of the line along the line of sight. All right, so this gets at one of the questions that was in the chat, and it's already been hit on 3 or 4 times by the previous speakers. This is a graphic trying to boil down this business about the sign convention in an interferogram. So we define the interferogram as being formed from the first image times the conjugate of the second being later in time, typically. And with the sign convention on the phase, this means that you have minus 4 pi over lambda times this phase range difference is 4 pi over lambda times the range at the later time minus the range at the earlier time. So these images down here are an attempt to depict what's going on. And it's a little bit, I have to say, it's a tiny bit confusing now that I'm thinking about it. But what this is trying to depict is a block of land here that's measured at time t1 that moves from time t1 to time t2, basically just vertically. It looks like it's displaced here, but this was just so that it was easier to see. This has only moved vertically on the left side over here. And what we are measuring is just this projection onto the line of sight direction. So in this case, as the surface moved up, we are measuring a decrease in the range from time 1 to time 2. Similarly, and this was related to the question in the chat, if at time t1 the ground is here and at time t2 the ground moves horizontally towards the radar but along the ground here, then you get also a similar decrease in the range along the line of sight direction. So these two, as depicted here, would not really be distinguishable in terms of horizontal or vertical. We just get the projection. And then here you can see the opposite over there. So this would be inflation or movement towards the radar and deflation, movement away from the radar. I hope that explains the question that was asked earlier. So in general, we don't measure interferograms that have exactly 0 physical baseline from time t1 to t2. It's very difficult to fly a radar, to fly over, especially from space, but even from aircraft with 0 baseline. So in general, interferograms have a combination of both topography and displacement in them. So there's a topography term and there's a displacement term. There probably should be a minus sign in here someplace, but let's not worry about that for now. So in general, once you go through the equations to derive the flattened interferogram, you would have the range change component and you'd have the topography component. So again, if the baseline were exactly 0, then this term would go away and you'd be left with just the range change. The baseline is virtually never exactly 0 because as you are up in space and you're looking across some finite degree of angles from near range to far range, the angle is actually changing. And if you're projecting the baseline onto a particular look vector at a given range, you're going to end up with some small potential component of a baseline if the baseline's, even if it is close to 0. So you can test your understanding of all that as you go along here. Let's talk a little bit about interferometric sensitivities. We say in general that differential interferometry allows you to detect millimeter level surface deformation. And it's much more sensitive to displacements of that level than a topographic map would be. So, and that's given by looking at basically the fringe rates or the ambiguity height as a function of phase as a function of height, comparing phase as a function of range change in the two cases. So this equation comes from some of the derivatives we took up above. You can derive it yourself, and it shows what the sensitivity is. Again, if the baseline is 0, then this sensitivity is 0. You don't have any sensitivity to topography at all. If the baseline is larger, you do have sensitivity. But you can see that the displacement sensitivity is independent of baseline. It's basically proportional to 1 over the wavelength. So if the baseline divided by the range is much, much less than 1, which is almost always the case, baseline is on the order of hundreds of meters to kilometers. And the range is usually 1,000 kilometers or so from space. So it takes a much larger change in H to get a particular phase change than it does a change in delta rho to get a particular phase change. So you're measuring differential phase in your interferogram. And in order to get a certain amount of phase change, which you know to millimeter accuracy, you have to have a large height change compared to a direct change in the range. Because one is a triangulation problem, the other is just looking at a difference measure. So you can play with that yourself. I've coded up in this cell below it, the actual equation that you see up above, and you can type in various parameters here yourself to look at these sensitivity equations. And you can see that the sensitivity radians per meter of elevation change is very low for this particular case, whereas it's quite high for the wavelength I selected here. So you're much more sensitive to a phase change, and you can test your understanding of that as you go along. For phase unwrapping, this is a huge topic that we don't really have time to cover in general, but all I can say here is that it is something that you need to pay attention to. The actual phase may be some nice continuous deformation pattern that you're interested in, but when you measure the interferogram, because it's a complex number that's delivered to you and you're measuring the phase by taking the arctangent of the imaginary over the real, you get a wrapped estimate. You don't get the actual physical phase estimate. And if you try to unwrap that signal, you will have to pick a point on the surface and make some assumptions and try to unwrap it to reconstruct this. And if you started here in the middle, you'd get this function. If you started over here, you'd get the same function, but at a different, as we call it, ambiguity level, different multiple of 2 pi. And so that can be an issue. And this is a simple, trivial example in 1 dimension with no noise. But in 2 dimensions with noisy data, this can be a very difficult problem. I think throughout this course, even though we don't really have time to talk about it in great detail, you will see examples of places where phase unwrapping is successful and unsuccessful. And there'll be some evidence of the different algorithms that you can apply in the workflows that we have to be able to solve unwrapping problems. The ISCE software has at least 2 and maybe 3 or 4 different phase unwrapping algorithms built into it that you can play with. There are a number of other interferometric error sources that matter and that you will see evidence of in this course. Propagation delay errors that Franz mentioned earlier from the atmosphere are certainly prevalent. It's one of the dominant error sources you're going to see. Troposphere introduces these from water vapor, and the ionosphere also. You'll see an example of both of those throughout this course. Phase unwrapping errors, I think you might have seen one in the example that Franz gave in the bottom southwest corner. There was a little patch of orange, tiny little patch of orange that looked to me like a phase unwrapping error. And then interferometric decorrelation, which we'll talk about in the second part of this lecture. There's a number of other sources that you can read about. I don't really have a lot of time to go into them right now. But in general, you can express the error in this range change that you're going to estimate in terms of errors in the phase measurement itself. Many of these things up here contribute to those phase errors. If you have an error in the DEM that you are using to remove the phase associated with the DEM, then that will lead to an error. And if you have atmospheric errors, that will also lead to an error. You may also have a baseline error if you're calibrated incorrectly, and that can lead to systematic errors as well. So just as a quick example, I don't have too much time to go into it, but here's an example showing two different reductions of an interferogram to remove the topography at a fairly large baseline over Etna using the best available DEM before SRTM was produced. And then after SRTM, you can see that many of the so-called fringes over here that might have been interpreted as deformation simply disappear when you use a better quality DEM. It'd be interesting to do the same experiment with the Copernicus DEM. I suspect some of the residuals here would improve using the Copernicus DEM. For the tropospheric noise, typically, because the troposphere lies between the SAR and the ground, we end up with artifacts. The troposphere is a turbulent medium, and it changes from one time to the next turbulently. So you end up with several components, but one of them is this sort of random, power law spectrum-like behavior of the phase difference caused by the propagation, the change in the refractive index in that phase that's propagating along. So in general, because this is so-called non-dispersive, this atmospheric differential delay term is basically added to the actual displacement that you're interested in. And this, therefore, these two are indistinguishable. So this is a noise source that you can't do much about other than just take a lot of data and look at it over time and try to estimate it out, or use a model of that if you have such a thing to remove it. There aren't really good models at that scale. There are models, however, at the larger scale, and the bulk tropospheric delay that is modulated by topography sometimes can be removed effectively. And this example Franz showed in his segment briefly, but basically here's a InSAR observation over Hawaii. The two main volcanoes, Mauna Loa and Mauna Kea, look like they're having big deformation episodes. However, if you look at the tropospheric model associated with those, they look very similar. And once you subtract the two, they disappear. So you can see that the path delay through the atmosphere is correlated to the topography in many cases, because you have a stratified medium that has, as you go up in elevation, you're going through less and less atmosphere. So you get this topographic correlation effect. So that's something you also have to take care of. And if you have a model, it's a very effective way of removing it in many cases. So for homework for this particular module, please go through the self-check exercises that are up above just to test your understanding. And you can do some pretty basic calculations from the equations in this notebook. If you want to do it in a cell here below, just create a cell and do these calculations. That would be great. If you want to do it on paper, you can submit that as well as a PDF or something to the homework. All right. Any questions on that? I will move to the correlation notebook. I know it's very fast and probably a lot of questions. Questions about the Copernicus DEM, you can get that from a number of places.
Yeah, I provided some information already. There were some questions about phase unwrapping, where there could resources. I provided the book from 1989, but there's probably better, more recent resources. I'm not sure if you know of a good overview paper. Howard's paper, but it's also from 1998, and I'm not sure how much he says about minimum cost flow algorithms.
Yeah, I mean, most of the papers are not as good as just playing with the software, you know. I actually think that by the end of this week, after you see a lot of the examples and then, you know, maybe change some of the parameters that are associated with some of the unwrapping, you'll probably get a better intuition than the papers necessarily will provide. I think Shannon Zebker is a good paper, and Mario Costantini has some excellent papers on phase unwrapping for minimum cost flow. So we can provide that resource later. All right, let's move on. All right, so let's talk about correlation. So if you studied the SAR notebook, part of the pre-course, you would have seen this figure. And it basically is trying to explain the fact that we have a coherent imaging system here. So we send a electromagnetic wave from the sensor down to the surface. It scatters off of that surface, but what it's scattering off of can be thought of as a collection of individual scatterers within a given resolution cell. And each of those scatterers is a slightly different distance from, let's say, a reference surface that characterizes that pixel. And it might have its own intrinsic amplitude and phase associated with it. And what we get in a coherent imaging system, like a laser pointer, when you shine it at a wall, is a speckle pattern created by this coherent sum of the amplitudes and phases of each scatterer multiplied by the intrinsic phase difference to that reference surface. So this complex sum gives you a net amplitude and phase for that pixel. And because each pixel in its surrounding area will have a different arrangement of these elemental scatterers, you're going to end up with sort of a random looking amplitude and phase from pixel to pixel. So, but what we do in interferometry is we take the difference of these two images. So here's the interferometric situation. In this case, we have two apertures. Looks like they're at the same time. You can think of this as one image taken from one time and another from another time, but with a baseline separation. If the angle here is very small, such that this reference plane is essentially the same reference plane, then these differential distances, and if nothing changed from one time to the next, if these scatterers are the same, you can, to first order, say that at these two different locations or times, you are seeing basically the same surface scattering, so the same speckle pattern. And what you're really measuring then from these two different geometries would be this difference in this range that you're measuring when you form the interferogram. So S1 has the amplitude and phase of the backscattering element times the propagation phase delay. S2 has the same amplitude and phase of the backscattering element times its propagation phase delay. So in forming the interferogram, to first order, the backscatter phase cancels and you're left with just this range difference that we've been talking about in the previous notebook from a geometric perspective. So that's sort of the principle here. In correlation theory, though, we explore the limits of that as we go on here, the limits of the assumption of sameness. So we can use a standard correlation measure, which is basically the product, the expectation of this product of S1 times S2 conjugate normalized by its power to define what the correlation of a given interferogram measurement might be. And for deterministic signals, this is clearly an easy measurement because if S1 and S2 aren't changing, then their expectation is equal to their value themselves. And if you calculate the correlation, you'll get a correlation of 1. So that's pretty straightforward. If they are not fixed, but they are random for whatever reason, then you're going to, in this expectation, you're going to get cancellation of these phase terms as you average over different statistical estimates of these phase values. So the correlation in general will be less than 1. So we can use correlation as an estimate of the sameness of our two images. There are reasons for lack of sameness. We call this loss of correlation or decorrelation. Thermal noise in the radar imaging system can introduce actual degradation of the signal. If you are looking at it from a slightly different viewing geometry, including the baseline, or if there are volume effects, we'll see some examples of that below, then the sameness does degrade. I said up above that we assume that they're the same to first order. Well, to the next order, they can change. And then, of course, if the surface is changing over time, then you will get a decorrelation signal there as well. Correlation is related to the phase error. We will see that below, and that then determines your height or displacement accuracy and your ability to phase unwrap. So understanding the correlation of an image, to me, having done this for many years, is sort of the first thing I want to do in order to assess whether I'm going to be able to do something useful with the data set or not. If the whole thing is decorrelated, just give up. If it's marginally correlated or correlated well in some places but not in others, then you have some hope. Some people use the term coherence, some people use the term correlation. It's really basically synonymous from the perspective of this class. So when we estimate the correlation, ideally we would, is there a question? No. Ideally we would have a statistical estimate of it. So we'd have an interferogram, and then we've had 1 million realizations of that interferogram with drawing from sample of the noise statistics, and then we could calculate the expectation. That way we don't ever have that. We have an interferogram and we want to estimate the correlation. So what we do typically is substitute that true ensemble averaging by basically taking a spatial expectation operator. So this expectation of S1, S2 star is estimated or approximated by basically a box of data points, pixels, over as homogeneous a region as we can find, and we estimate the interferogram that way. So the correlation looks like this in that case, and it's just the summations over these boxed regions. So this is not a unbiased estimator, and you'll have a little test up there to check your knowledge of that. And you can look at, if you do some sort of simulations of what correlation would look like as a function of the actual correlation, given the size of that box. When we say looks, you might have gotten this from the SAR notebook. What we're talking about is the size, the number of pixels that you're averaging in that box up above to estimate the correlation. So this is the probability of the actual correlation given what the correlation, as a function of the correlation it is, given that you're using an estimator to estimate it. So you can see that in the case where the correlation is actually 0, and you do this experiment to calculate what the correlation distribution function would be in the estimator, for 40 looks, you would, meaning you average 40 points together, you would see a distribution of correlation values that looks something like this. So if you pick a place that is totally decorrelated, you make a lot of these estimates and plot them as a histogram, this is what you might see. So you can see that the estimated correlation is not by any means 0. 0 is over here. It's something like 10% or something like that. If you have 10 looks, many fewer looks, a smaller box size, then you get an even broader distribution, and you bias your estimate of the correlation even more. So many people, when they first get into the field, they see they make an interferogram, they take a few looks, they look at the correlation map, and they see a correlation they say, ah, that must be good fringes there because it's got a correlation of 25%. But then they look at the fringes and they can't see any fringes, and they puzzle as to why. On the other hand, as you get towards higher correlations, you can see that these histograms are much more tightly peaked, and that you get a correlation estimate that's much closer to the actual correlation itself. But it is also biased, even at the higher correlations. So be careful is the answer there. So here's an example of a couple of correlation maps that you might find from making something from an interferogram. This happens to be from ERS when it was in its one-day mode for part of the mission, and then also in a 6-month interferogram. So you can see this happens to be water over here. These are mountains and alluvium over here. This is a big sand dune called the Algodones dunes. These are agricultural fields. And so you can see lots of interesting features. And even in one day, there's significant decorrelation in the mountains. There's quite a bit of activity in these fields. So you can see that correlation can actually be an interesting measure, not just a noise source, decorrelation. You can see that the Algodone dunes remain mostly correlated over a day, but there's some interesting features in here that I think you will be, if you took the pre-course survey, you were asked about that. So hopefully you took a shot at that. Over 6 months, you can see other interesting features. You can see a big decorrelated region over here. That's the Colorado River. You can see the agricultural fields very much decorrelate because there's been a lot of activity there. The dunes even stay somewhat correlated over time. Alluvium actually appears better correlated in many places, which is an interesting phenomenon that you can think about. So correlation has a lot of information in it, and knowing something about the surface and measuring the correlation can tell you quite a bit about what you're looking at and what problems you're likely to face. Correlation and phase error are related by this equation here, in the limit where the number of looks is greater than about 4. This is a calculation that shows you sort of the more general case where you have the number of looks for each curve, correlation, and the phase standard deviation. So clearly, the better the correlation, the lower the noise is on your phase measurement. And so you always want to go with the best correlation that you possibly can. All right, so quickly, we're going to talk about a couple of different phenomena that lead to decorrelation. The first one is thermal noise, as I mentioned above. You can go through these equations, and this is the deterministic signal and the thermal noise source. And if you assume that the noise is decorrelated, is uncorrelated from one time to the next, then you can go through this equation and show that the thermal noise correlation is proportional in some way to the signal to noise ratio of the system. So if you have a particular signal level, a particular noise level, you can predict what the correlation is going to be. So clearly, if the SNR is low, then the correlation is going to be low. If the SNR is high, then the correlation is going to be high. So that's, and sometimes you can't control the SNR because of slope effects and things like that. And you can test your knowledge of that concept in that experiment there. So baseline decorrelation is another factor, and that is described here. As I described earlier, to first order, we assume that these planes are the same, but to the next degree, they are slightly different. And you can go through a calculation that shows what the effect on the correlation would be as a function of baseline. And after a lot of calculation, you end up with a very simple expression, which is given by this, showing that the correlation is basically 1 minus the perpendicular baseline divided by some factor, which we call the critical baseline. And that's expressed over here. So if the baseline, the perpendicular component, is 0, then you have perfect correlation for this term. And if it reaches the critical baseline, then you get no correlation whatsoever. So in answering, I think, a previous question, you would like to have the perpendicular component of the baseline to be relatively small relative to this critical baseline, such that the correlation is high for your measurement to keep the phase errors down. And note that if there is a slope component to it, that will modulate the critical baseline. And the higher the slope, the shorter this critical baseline becomes. So you need to have a smaller actual baseline in order to accommodate a particular noise characteristic as the baseline gets smaller. So not time to really dig into this, but from the very first spaceborne interferometer, CSAT, which preceded ERS, we have some theoretical versus observed measurements of the correlation as a function of the baseline. And the explanation for this difference is probably that the bandwidth of the system, the resolution, was not well characterized. But the point is that it is a linear behavior as a function of baseline. There's another related decorrelation term called rotational decorrelation. And that is similar to the geometric decorrelation in the previous example, but in the other dimension. So this plane is no longer exactly the same aligned in the along track dimension. And so you can calculate, you can show that that's also kind of a linear change as you go, as you point more and more off angle. So this rotation angle, as the rotation angle gets larger, then the correlation decreases. And of course, since it's dependent on the beam width of the antenna, the wider the beam width, the better you'll be. And for L band, typically you have a wider beam width than for C band for a given antenna length. So the correlation at C band is more sensitive than L band for all things being equal. A convenient, intuitive way of understanding baseline decorrelation is to think of the pixel as an antenna. If you took the SAR, looked at the SAR theory module, you'll know that the antenna beam width is basically lambda divided by the dimension of the antenna. So if you think of this as all these scatterers contributing to a wave that's re-radiated back to the spacecraft, then it has its own intrinsic beam width, which is lambda over the resolution cell size in this dimension. So that beam width then will determine what the critical baseline is. The critical baseline would be defined by, at the distance of space, this the angle subtended by the distance that this angle subtends. And that's a useful concept for understanding volumetric decorrelation and point targets. So normally, for a distributed set of scatterers on the ground, you're going to get some re-radiation pattern similar to what I just showed in the previous figure. But if you have a vegetation canopy and a resolution cell of a particular range dimension, you're actually going to get scattering from everywhere in this volume. And that means that the effective size of that antenna that's radiating back to the antenna is much longer. Which means that the angle subtended by that antenna will be much smaller, meaning the critical baseline is now decreased, similar to if you had a slope on the surface, which extends the size. So slopes and canopies can decrease the critical baseline and therefore decrease your correlation. In the opposite direction, if you only have one scatterer that's in your scattering element, like a corner reflector or the edge of a building or something, then that resolution element effectively collapses to an infinitesimally narrow resolution element. And the re-radiation pattern of that is much broader. So now you have no longer the same constraints that you had before on the correlation. And that's why for permanent scatterers, which are like these point targets, you end up being able to use data that have very long baselines, and that indeed they stay correlated over time as well, because they're permanent scatterers. So hopefully that's a little bit intuitive. There's an equation here for volumetric decorrelation if you're interested in looking at that later. Then, of course, there's temporal decorrelation, which is difficult to characterize because the natural surface is not well behaved from an interferometric point of view. But there have been some simple models that have been developed that can help you understand how correlation might change as a function of wavelength, given a certain amount of RMS motion. So this means that from one time to the next time, if the tree went from one orientation to a new orientation that was changed by around 1/10 of a meter at L band, you would lose all your correlation. If it's much less than 1/10 of a meter, then you can maintain correlation. And you can see that the shorter wavelengths tend to decorrelate faster for a given motion because of just the nature of the wavelength being interacting with things at the wavelength scale. The wave interacting with things at the wavelength scale. So in general, the correlation is a combination of all of these different components, the SNR component, the geometric component, the temporal component, and this volumetric component, which can be thought of as a form of this geometric component. There's also rotation in there in the geometric component. So that's a very quick whirlwind tour of correlation. Here are some interferograms that are made from an airborne system that happened to have at the same time a C-band, L-band, and P-band system. So 5.6 centimeter wavelength, 24 centimeter wavelength, and 75 centimeter wavelength. And these are the phase measurements of the interferogram, and these are the correlation measurements from that interferogram. And you can see this happens to be over forest, so you can see that the correlation stays better at the longer wavelengths because you're less interacting with the shorter wavelength elements, as the shorter sized elements in the canopy. All right. And then for homework on the correlation, there's 3 relatively simple problems. Just go back into the notebook and calculate some things that should be pretty straightforward. Again, you can either create a cell that does the calculations directly, or you can write them down on a piece of paper and submit a PDF as homework. All right, so I know that was very fast and I still took an hour, so my bad, but thank you for listening. And if there are questions, I can stay on and answer them in the chat. Today, I won't be at the office hours in the afternoon, but tomorrow morning at 7, I will be in the office hours in the morning. So feel free to talk with me about anything at that time as well. How do we get the self-guided multiple choice questions to work? So basically, as I said at the beginning, if you just go up to the top of this notebook and just click on the cell and click on Run All, it will run every cell in this notebook. And that will then set it up so that you'll see these selections and your choices. So that, I mean, it works for me. It should work for everybody. Okay. All right. Thank you. And I think, is there another break now? It probably is.
Yes, we have supposedly a 10-minute break. Wow. Oops, that didn't work out so well. Yes, 10-minute break. We are, let's see, how much behind?
I think we're a half an hour behind.
Okay. Well, for symmetry, it makes sense, I think, to have a 10-minute break until 30 minutes after the hour, and then have Haresh talk about strip map processing.
Yes.
So Paul, do we want to finish at 2 sharp or no? We can go until it finishes.
Well, as you know, I need to go and run that meeting that you would be in otherwise. I don't know that we need to end at 2 sharp. If you can end as close to 2 as possible, that would be great, because people may have other plans and it's very late for some people. But since it's not your fault, you should just go to a point where it makes the most sense to break.
Okay, so I'll try to at least make sure that they are familiar with the notebook and we run through something. And I have another one pre-run. So if I realize that it's taking too long because of the compute environment as well, then we may just break it and ask them to run it on their own.
Yeah, I think that's likely to be required. The SLC computation is pretty slow. Okay, great. So we'll come back at 1:30. So maybe I should put that up.
Yeah, so enjoy your break. Keep the questions coming. There were lots of questions in the chat. Thank you for all of those. If you haven't posted questions yet because you didn't dare, you can also use lots of questions in there. So please, please put them in. Also, feel free to speak up if you have questions while a speaker is going. Okay, see you all in 10 minutes.
No, Paul, are you there? Can I go ahead?
Let's get going.
Oh, okay. Let me first allow Zoom to share my. Looks like I have to quit actually to let Zoom share.
Oh, you haven't shared Zoom?
Looks like not in a. Let me.
You have issues sharing?
Let me 1 second.
Yeah, I think it's his Mac setting. He can change the permissions.
I believe I have to quit and come back.
Yep.
Yeah.
Yep.
So while Harish is getting ready, make sure the next section is section 1.4. So you can go to UNAFCO section 1.4, strip map data processing and interferometry, and then pull up the notebook stripmap app.ipy notebook.
All right, do you guys hear me? And
Yes,
do you see my screen? So as
Franz, you're going to have to stop sharing your screen.
I think that's Harish sharing.
Oh, that's Harish? Oh,
yeah.
That's me.
Okay, okay. Then good. Yes, we can see it.
All right, great. So if you go to the Geosync repository and go to UNAFCO, go to 1.4 strip map data processing and click on strip map app notebook. it should basically open the notebook that we are gonna talk about.
So Haresh, we see your Google Doc.
Oh, really?
Syllabus.
Yeah, you might not be sharing the right window.
Okay, let me share the right window then.
It looks like the Strip Map app notebook requires a kernel change, which is kind of fun because then we can practice how to do it.
That seems true.
So Gareth, did you put another notebook in 1.3 that will be used later? Because there is, or is that a vestige of some past organization?
Wasn't me.
Yeah, there's a notebook interpreting InSAR data, and that is going to come later, isn't that true?
Yeah, that's in 2.1 or.
Yep.
So is it in two places? I should just delete the one in 1.3?
Yeah, it's harmless, I guess.
Okay. Somebody asked, so.
Yeah, good catch. Thanks for pointing this out.
The only thing I would advise Suresh would be to zoom in a bunch.
Yeah, you'd have to zoom in some. And so have you guys opened up the InSAR app notebook yet?
Strip Map app.
Sorry, Strip Map app notebook. Did you get an error message that says that it's set to the wrong kernel? Yes, excellent. Haresh, can you
All right. So yeah, I hope, sorry about the technical issue. We are usually using WebEx at JPL, and I recently changed my laptop after a few years. So my Zoom setup has changed. So we are going to talk about the first module with data processing with iSoftware. I assume you guys already opened this notebook, and probably you see a problem with the kernel. So if you go at the top, let me zoom in a little bit more so you guys can see better. Is that better, Gareth?
A couple more probably would be even better.
Is this
Yeah,
better?
that's great.
Yeah, that's better.
So if you go to kernel, change kernel and choose UNAVCO, just to make sure that we are using the right environment where we have the iSoftware set up for this course.
Did everybody get that? How to reset the kernel?
Kernel, change kernel, UNAVCO.
Excellent.
All right, let me just open the chat window somewhere so I can see a little bit of the messages over there. And I'm sorry that I could not attend the pre-course sessions. I'm wondering if Franz, if you guys talked about the Earth Data user pass. I assume so.
We talked about the username and password that for Earth Data.
Okay.
And
so,
I think some of you needed to already set up a netrc file for some of the pre-course activities.
oh, wonderful. So just a reminder then, if you open a terminal by in the main page of your OSL environment, just say new terminal, it would open a terminal like any Linux machine that you have probably used, and then you have to have, with whatever tool you are comfortable with, but you have to have a netrc file, .netrc file that has your username and your password. I also just posted in the Slack channel, in the search data channel, that as a one-step instruction to create this file with one comment. So you really need this file. It should be at home.netrc, and it must have the same structure, basically machine user.earthdata.nasa.gov. Login would be your Earth data, login name, username, and password will be your password. So that's one thing that you need. Specifically, ISCE is going to use that for downloading any DM. You also need the same thing to download some data. So let me go ahead and talk about this notebook. This notebook is about the street map data processing. So you might say, what's street map? Probably somewhere in the pre-course we might have some information about different imaging modes for radar. And one of the very basic traditional modes is street map. To compare with what TOPS mode is the operational mode for Sentinel-1. So you might have, since Sentinel-1 is really the live system right now, and we have a lot of data, so you might have heard TOPS. But street map is really the simpler imaging mode where we have the radar on a platform like a satellite or an aircraft. It's pointing to a fixed direction, so the illumination on the ground is not going to change. We have a fixed angle called actually squint angle, where we move the platform, and by moving we are imaging a swath on the ground, which you see is a usually narrow swath. To increase the width of this swath, there has been a lot of work done in the SAR community. Before TOPS, we had ScanSAR, which I'm not showing here. And then there is TOPS mode, which we will get to tomorrow. And there is also SweepSAR, which we are not covering in this course, but that's the technology that NISAR is going with. But since I'm showing this figure, let me explain a little bit more. The need was, okay, we are getting SAR images, we are doing our science or application with it, but we need more. We need more swath. Since the radar is anyway flying, let's get more data. So to increase the swath, we need to change the elevation angle, which is the angle between the beam and the nadir at the satellite position somewhere here. So we need, as it's moving along, it's rotating and taking some data, it changes the elevation angle, illuminates another swath, and then as goes along, illuminates another swath. So with those colors, you see how at any position that the radar was, which subswath was illuminated. So it's more complicated. The processing is different. But today we are going to talk about the simpler one, which is street map. With that introduction, so it should be clear that we are talking about street map data processing. The technology has been used in many radars, operational radars before, such as ALOS-1, which we are going to talk about today more, NVSAT, ERS, a lot of TerraSAR-X, as well as Cosmos SkyMed. Even Sentinel-1 has a street map acquisition mode, which they have actually acquired data, not too much, but in certain regions, there are some stacks of the street map data as well. So ISCE, as you will hear more about it in this course, is a modular software. So there are core modules written through years, really, by many experts at JPL mainly. And there are some wrappers around those modules, which are Python wrappers. And those Python wrappers are actually giving access to the lower level modules, where basically you can write your workflow in it. So we have provided a few workflows, or an application, which is one of them is Street Map app. So that's an application in ISCE2, which is used for processing street map data. The application is going to take either raw data or even SLCs, depending on the different sensors, is gonna focus the data using an old focuser at JPL called Roy. It's a range Doppler focuser, and then it's gonna do geometrical computation to find the offsets between two SAR images, co-register them, resample them, and then take out the phase due to the topography, and finally form some interferograms, do phase unwrapping, and geocode the final data. We have also some correction modules like ionospheric phase estimation, for example. If you have your .NET RC file, you don't need to populate these two fields here, but basically this first cell, go ahead and run it. It's gonna set up just your environment where it's gonna be the home directory, and if you have the .NET RC file, it's gonna look for the user path, and from now on use it for some of the downloading. By the way, regardless of you put the user path here or not, for DM download at the middle of this course, you will need anyway that .NET RC file. This cell is gonna set up a function that we can call later for setting up the configuration of the input files for Street Map app. In ISCE2, for different applications, we have basically some XML files, which I'll show in a bit, and this function is gonna automatically set up those files. Go ahead, if you are following the course right now and you want to run it yourself, you can go ahead and run it. And then the next one is just gonna check if the home directory and process directory already exists. If not, it's gonna set up the processing directory for you. I have chosen this to be somewhere in work, Hawaii LS1. And the reason for that is we are gonna process a pair of LS1 data over parts of Hawaii island, the big island in Hawaii. And we have already identified two LS1 raw data sets, which we can just get with a wget command. Those data are sitting in an ASF archive, and you need the Earth data user and path, as I mentioned before, to download them. In my case, the data already exists, so the download is not gonna be basically done for me because I have already downloaded the data. But for you guys, probably it takes some time. And whenever a cell is running, if it's taking some time, you will see that a sand clock basically at the top of your browser. That means that cell is still running. Since we don't have much time, I'm not gonna wait, but as you can go ahead step by step, either now or later yourself. And while after the data is downloaded, you will see that you will have two zip files. I'm gonna talk a little bit more about them and what is inside them. If we need to unzip them, so I'll go ahead and unzip them. Actually, they have been already unzipped, so I'm gonna stop that one and even this one, and just take a look at this one. So there are multiple files inside the unzipped file, and one of them is just a work report. We have also imagery files, IMG. The data is provided in two polarizations, in this case, HH and HV. There are some description of like it's Elos Pulsar. Here's a complete description of whatever decoding of those names, basically. The polarization, the image data, the Elos Pulsar representation, the orbit number, the frame number, and the production level, which in this case is 1, 0. So it's raw data. And at the end, the descending or ascending A or D, which represents whether the satellite was in its ascending path, basically from going from South Pole to the North Pole, or it's in the descending path, which is from the North Pole to the South Pole. If you don't have the .NET-RC files set up, don't worry. We can I can make sure to call in the office hour today to have those set up for you, or on the Slack we can do that. I would recommend to just pay attention to the different steps that we are gonna go through today together. If you look at that work report, you will see that there are some general information of what is really there when it was processed, what's the acquisition date, some information that you might not necessarily need. For me, I just needed to extract what are the acquisition dates. Based on that, we are making two basically directories, and we can move those unzipped data there, and make sure to run this one to go back to the process directory, and you can check where you are. So we are at the process directory. Next is to set up the inputs for the configuration, basically the inputs for the Street Map app. We have one, as I said, I'll just go ahead and run this cell. So it's writing reference.xml, secondary.xml, and streetmap app.xml. As I said, we are running the streetmap app.py, so we need one configuration for that. That configuration looks like something like this one. It tells ISCE that, yeah, the application is streetmap app, and it's an InSAR workflow. The sensor is ALOS. Then, this is wrong. This is alt. This should be reference. In the actual configuration, it's actually correct in the function that we write this automatically. Sorry about that. Let's just fix this. Secondly, we need to point to the reference.xml and secondary.xml, which if you have run this function, it already creates it for you. Just to make sure that I'm not losing you, I want to go back to the terminal. For those who are familiar with Linux, which I really hope that most of you are, or at least some basic knowledge, because our software works in that environment. Here is the terminal, again, that you can open one by going to new terminal. You can open one, and by running those few cells, you should now have a directory called work. And so now I am at this path, and I have Hawaii ALOS1. So in Hawaii ALOS1, there should be some streetmap app.xml. So I can just print it, or I can actually a little bit better, maybe just do it. Basically the same thing that we discussed there. That's the input configuration for the streetmap app.xml. This is important because this is what is going to tell the application what to do. Actually, by mistake, I have it to do split spectrum, which I don't want to do today. So I'm gonna make that false, and there is do dispersive. I'm gonna do that false. It doesn't matter really. It's just extra steps that we will get to it in future courses. But anyway, those few steps that we talked about is gonna create those directories, download the data, and create the configuration files for you. Once we have the data and we have the configurations, then we can run the software. In this case, our StreetMap app application. If we say what are the StreetMap app.py-help-steps, it tells you some general high-level help about this application. It says that it supports these sensors. So it's not only ALOS, there are many more sensors that it does support. And also the other important thing is it tells you that how to run it. You can always say, as you will see, to start from a step and end at a specific step. What are the steps? The steps are from startup all the way to end up. We are gonna go through all these steps one by one, and you will see that we have the pre-processing, cropping, forming the SLC, cropping SLC, doing some geometry computation, resampling, and more until the interferogram formation, filtering, multi-looking, unwrapping, and geocoding. All right, so we can go ahead and look at the steps. I think we already did that one. I'm gonna go to this first step, basically, which is pre-processing, startup to pre-processing. All it does is it looks at the data that we downloaded and unzipped, and it's trying to extract the level 1, 0 data. It's swapping some bytes. Basically, it extracts the data that as was provided by the data provider and puts it in a format that ISCE can understand. And it creates a file called in this directory and called .raw. So all what we are doing, and it extracts all those information that one would need to focus raw data to the SAR image. And that includes like what's the PRF, which is the pulse repetition frequency, the start time, the exact start time of the raw data. It's very important to know the timing, because that's how we are gonna look at all those pulses one by one and compress them in the range direction and then in azimuth direction. What are the number of lines and few other information. So basically it looks at all those lines line by line for both images. And now we are at the second image, actually second raw data. We still don't have image. If we follow the SAR terminology, now we are working on the secondary data set. Again, goes line by line, and finally creates the .raw file for the secondary image somewhere. All right. The good thing is when any step is done, the application is gonna report this message at the very end that says the remaining steps are in order, whatever is remained. So in this case, now we have to run crop raw. So crop raw is really when you want to subset the raw data. You can do that. You can crop you can just put in some lat long bounding box in your XML input XML file, and the application is gonna crop the raw data for you, even before focusing. So if we check whether this folder is created, yes, it is created. That's the main raw data, and some basically artifacts that is coming with it. In particular, ISCE requires the metadata, what's the data format for this, what's the number of line, number of pixels, etc., etc. And since we have some GDAL compatibilities, then we have this VRT file. If you have looked at the pre-course about GDAL, this is just a text file that tells what is in this data set. So if we go ahead and run the next step, it won't do much because we didn't ask for any subsetting, but you could put this line of code in your input XML file somewhere if you want it. Somewhere here, you could add that subsetting line if you want a subset for your own case study, and that would subset it for you. Even the steps that we haven't requested, just make sure that you are actually running them step by step and you are following each step. Otherwise, you might get something may break. So I'm gonna go ahead and run the next cell, which is obviously form SLC. So that's the step that takes the raw data and tries to focus the raw data to SAR images, single log complex data. And this process is done for both reference and secondary data. It starts with the reference and it ends with the secondary. You might see some general information about that the processor is using. The algorithm, as I said, it's a range Doppler algorithm. So it's doing the range compression first and then the azimuth compression. Generally, it's fast. It shouldn't take very long. We are already at some range migration step, which probably in some of the, I think in the module from the pre-course module that Paul mentioned about the SAR focusing, there is a more detailed explanation of what is really going on when we take some raw data and form some image, some SLCs. Is there anyone that is following and trying to run the notebook with me, or yes? Okay. All right, great. Wow, wonderful. Awesome. I see a lot of people are able to run the notebook, so that's really good. I believe we are already working on the second image probably. Yeah, so thanks, Franz. Yeah, the SAR theory notebook, basically, to be more specific. Yeah, so verify DM. If it fails for you, that means that you don't have the .netrc file. Make sure that you make the .netrc file. I also included in the Slack channel, there is really just one command that you could run, and that would generate the .netrc file with your login password. Yeah, so you don't have that file, so you have to create it. You have to, while the focusing is going on, again, make sure that in your OpenSAR lab environment, you go to new terminal. So you open a new terminal, and in your new terminal, you can use Vim or VI or whatever that you are comfortable with. Create a file and make sure it has these things. And instead of this, you should just put in whatever your username is. I don't know what is your username, but whatever is, just put it in, and whatever your password is. So I have the DM already, so I'm not worried about that. But for you, you have to make sure that you do that. All right, so the focusing is done. After focusing, let's just make sure that, yeah, we have the folder called 2011-01-19 -SLC, and we have the .slc, which is the SLC image, and some metadata, one VRT file and one XML file. If we just run a simple GDAL info on that .slc, it doesn't have the geo information, but at least it will tell you, what is the size of it, what's the shape of that data set, basically. And if you want to just open it, there is few very simple Python lines to open the data set with GDAL. If you haven't used GDAL before, we have a notebook in the pre-course that you could take a look to get more familiar with the software. It's very powerful for raster data and remote sensing data analysis. And you can simply say import GDAL. Once we have imported, you can just say GDAL.open whatever file that GDAL supports. Since we created a VRT file, as I showed you here, then GDAL does understand our SLC. Then we can just simply run this. And if you look at the script, it's very simple. I just tell it to, because these are big images, I don't want to read the entire image to memory. So I just extract a subset, which I specified here, 5,000 line by 10,000. 5,000 by 5,000 window. And I make I'm using Matplotlib just to make a figure. And here is the amplitude and the phase of that subset of one of the SLCs. So not much really to see, except that if you, as probably you have seen in Paul's introduction, the phase of the SLC is just random phase. You don't see much in it. It's just noise, right? But that's why we are doing the magic of interferometry, as you will see at the end of this notebook. The amplitude makes more sense. We are looking at part of the island. So we see the ocean is dark and land is, it's not probably the best color scale to show it. But anyway, it's clear that the ocean is dark in our image and land is bright. So we can go ahead and run the next step, which is crop SLC. And for that, we don't have much to do because we didn't ask for it. And then next step is verifying the TM. It's gonna tell me that, yeah, I am all good. For you, you must have the you must have the .NET RC file to be able to run it. So this step takes some time. I'll go ahead and run it and I'll explain what is going on. In the meantime, let me just take a look at the chat. There is one. Is there any question for me?
Yeah, there's a good question about native Doppler versus zero Doppler. I think Gareth may have, or it might not be zero. Yeah, I'm not sure if you want to address this a bit more. There was a question about, what is the real difference between native Doppler and zero Doppler geometry? And it's, yeah.
Very good question. I didn't look at the answer, so I'll just go ahead and explain a little bit more. Maybe I could go back to the very top where we had the figure. So in this figure, it might not be the best figure, but we have the direction, the long track direction or azimuth direction where the radar is moving on a platform. So that's the azimuth direction. And we have the cross track, which is just perpendicular to the along track. So that's really the zero Doppler geometry. That's zero Doppler. And the reason for that is if you look at the Doppler profile, of all the ranges that we get. Think about the radar echo that you are getting, you are sending something and you are getting from different ranges. So the Doppler, once you get to that point, is zero. So that's why it's called zero Doppler geometry. All right. So it's basically the look direction is perpendicular to the along track direction. It is possible that the sensor is not, it's strip map, it's fixed the direction of the look, but it might not be fixed to a zero Doppler. It might have a squint. Imagine that in this case, instead of looking right across, it would look a little bit forward or a little bit backward. Actually, the tops has some squint, but it's rotating, it's more complicated. In strip map, native Doppler, it would be somewhere fixed. Well, a native Doppler could be a zero Doppler too. So you could have a radar that natively it's fixed to zero Doppler. Or no, the data is acquired at a different Doppler, at a different squint angle than zero squint angle. And you could focus the data and the output grid still could be zero Doppler. So really what the grid of the image is slightly different from what was the acquisition geometry. So basically, really the zero Doppler or non-zero Doppler explains what is the geometry of the imaging, and also later what's the grid or the geometry where the image is provided at, which might be different from the acquisition geometry. So I hope that explains a little bit. Yeah, we definitely need to know the geometry. So the question is, that means that we start from the knowledge of the amount of squint, right? Yes, absolutely. We need the positions of the sensor and the attitude for the best quality SAR imaging, and later on interferometry as well. By attitude, Doppler means attitude. From Doppler you can get to attitude. From attitude you can get to Doppler, sort of. So yes, we need to know that squint. We need to know what was the geometry to focus to. So we are definitely keep tracking of all those information through the processing. All right, so we got, sorry for scrolling, but the topo is running. Let me tell you what is topo doing. So we are at this step that we are running. Oh wow! Actually, topo finished. So that's great. Yeah. So I assume probably your DM is not there, Jack. It's okay. Let's make. Can you make sure that DM is there? Basically, if you, yeah, all right. So we are at the, I'm sorry. Must be a figure somewhere. I'm looking for the figure to explain. All right, so we are at the SAR sensor position, and we have two images. We want to co-register these two images. First, we start from the SAR sensor positions, and for every cell in our image, we know the start time and we know the starting range. And from there, and also we know, so just let's start with the first cell of our image. We know the start time, we know the start, the sensing start, and also the start range. And we know the position of the satellite because we have the orbit files. We can start from that position and go find the target position on the ground, just based on what was the range, what was the time, what was the Doppler, and also given the knowledge that we have about the ellipsoid, which in this case, our orbit was given in a WGS 84 ellipsoid. So we have enough information to look at these actually three equations, which are called range Doppler equations, in which we are solving what we know is the sensor position, and what we are solving for is the target position. It's a nonlinear equation, but it's very easy to solve, and with few iteration we can get to the unknown, which is the ground, the point on the ground. So after running topo, which should be really the actual name should be RDR to Geo, radar to Geo transformation, we have some files in a geometry directory called lat, which represents latitude, longitude, and also we have LOS, or line of sight, which is two bands of the, I believe, heading angle and the incidence angle, as well as the height or topography in the radar coordinates. If we just take a look at those geometry files, we can see that, just take a look at it, we have the lat, long, and height. That's where the island is, so you can see it in the topography. But this is just pure geometry. We are not looking at the data at all. We are just using metadata to compute geometry. That's why even over ocean, we got every pixel, because we don't care about the data yet. After running topo, we need to run now the inverse mapping. For topo, or for the previous step, we were starting from the sensor, from the reference orbit, and we got to the target position. Now, we are gonna start from that position and compute. This time, we know the target position, and we have the orbit of the secondary image, and we want to see at that target where basically the secondary image in the grid of the reference image should have been. If it would have been there, then everything was aligned already. But usually that's impossible. They are not on the same page. So that's what we are computing. We say, okay, from the reference image, we got to the target. Now from the target, at the orbit of the secondary image, we go back and we compute what should be the range and azimuth time for the same target. Usually it's not at the same place that the secondary image is formed, so we need to resample it. And that's really just the basic of the co-registration and the resampling. So right now the Geo2RDR is running, which basically transforms back those coordinates to as I mentioned, and it gives so the difference of that range that we computed to the secondary image and the range of the secondary image itself gives us the range offset, and the same for the azimuth direction gives us azimuth offset. So this is called geometrical co-registration, really. Just using geometry without looking at the data, we can say where the grid should be and just take the secondary image, and resample it to that grid. So that's why the Geo2RDR finished, and now we are at coarse resampling. I should have shown this one for the Geo2RDR. So basically, we had the first orbit, and we computed the this range 1, and then we computed range 2, and the difference is range offset. Also, the difference is the range, the delta range that we are gonna use. If we convert it to phase, that's the geometrical phase. That's the phase due to the topography, and basically that's the phase due to the baseline separation between the two orbits. So just an hour ago, Paul showed you that some analytical equations. If you would open this, and there were some somewhere there were some even approximation. If you want to approximate that with baselines, all days we were doing those things even for in the software, but now the orbits are so precise that we don't need that anymore. Just using geometry, usually we can get to enough information to basically flatten the interferogram. So that conversion of the ranges the range difference that we just did would give us the geometrical phase that we can remove from our interferogram later and get the flattened interferogram, which means an interferogram which doesn't have topography in it. So basically this gives us the offsets, the amount of pixel shifts between the reference and secondary images. And if you want to take a look at it, here's a simple script that tells you how many pixels these things need to be shifted pixel by pixel. Basically, the secondary image needs to be shifted to the reference image. Once we know the amount of the shift, then we just do an interpolation. It's simple interpolation. Usually we do a sync interpolation. It's complex data. Here is it running. It shouldn't take very long. And by running this step, basically we are taking the secondary SAR image, we are taking the azimuth and range offsets, and we are resampling it to the grid of the reference image. So that would give us the co-register SLC or the resampled SLC. So how are we doing? Is there anybody that's still able to run, or all stopped at topo? Okay. All right, great, wonderful. Okay, topo is working, but still going on. Yeah, so topo is probably our most expensive step. I was surprised actually it went fast. Thanks, Franz. So the instance worked good. Oh, Gareth got an interferogram. You're too fast, Gareth. Any question for me so far? If I missed any. Okay, I see Harvey's. Is this area the vegetated area or rougher than the area of bare lava? Okay, I don't know the question, so maybe somebody should tell me. I assume there was a question before that then. All right, this step finished. If you elaborate the question, I didn't understand. Perviz, I can answer, or I'll try. There should be a co-register SLC by now, and we can take a look. It's still probably similar to the reference SLC. Well, it's just part of the island, and still no interferogram. All right, so we are gonna run misregistration. I'm gonna just run the cell and explain what is going on. As I said, all what we did was geometry. We were not even looking at the data, and we said we want to trust the orbit. Well, orbits are really good these days, but okay, anything has its own accuracy, and we are going to trust the metadata of the sensor as well, like what was the starting range. So just with metadata, we computed the geometrical offsets between the reference and secondary image. But in reality, that might not be basically possible always. And the reason for that is Okay, this is going on. The reason for that is, well, we are propagating through not vacuum, but an atmosphere, and we have ionosphere and troposphere. So the range that we started with itself might not be precise enough. We have done a lot of work on understanding that impact last few years for ISAR, actually, where we have L-band, and ionosphere is very important for L-band. So the range could be off, or the orbit could be off. The timing of the clock could be off. Again, modern sensors, any sensor-related information these days are pretty good, but there are environmental effects. So that's why after running the geometrical offsets, we are running this step for estimating the misregistration, where we take the reference SLC and we take the co-registered secondary SLC and we cross-correlate them. So by cross-correlating, we are basically looking for shifts between them, just based on the data cross-correlation itself. So that's right now, there is a very old software at JPL called AMCOR, or Amplitude Cross-Correlation. Right now, AMCOR is running, and it takes chips in the reference image and takes basically a window of the secondary image, cross-correlates it, cross-correlates the search window over the reference window, and every time that it cross-correlates, it outputs a correlation. At the end, we will end up with a 2D correlation surface, and usually we upsample it by a factor of, I don't know, 32, 64, and we look for the peak of that correlation surface, and that's where the maximum correlation exists between those two windows, and that would tell us basically the amount of the shift that existed between those two pixels. So basically, no DM assist. Yeah, this is what all I talked about is DM assist co-registration. Maybe other softwares call it DM assist co-registration. Yeah, basically that's the same thing. The geometrical co-registration is DM assist. But it could be inaccurate in some cases, depending on the data sets. In C-band, actually, it's pretty good. For Sentinel-1, we probably, at least in range direction, it's really good. In azimuth, there is little issues, but it might not be due to the DM or the approach. It might be some other detailed stuff that I don't want to go through right now. But yeah, all the geometry that I talked about is DM assist co-registration. And so after this step, we end up with some estimate of the misregistration. And we actually usually take only a constant shift for the entire image. So it's basically these two numbers, actually. In this case, we estimated the range shift to be around 1 pixel and the azimuth shift to be around ½ pixel. Actually, for this specific example, later we found out that this 1 pixel is mainly dominated by ionosphere. So now we should have this directory where we are storing those two numbers, and we can even extract it if we want a little bit using ICE functionalities here. For the first time, if you want to take a look, we import ICE like a Python module, and we say from iceopt.stripmapproc.streammapproc, import that module, basically instantiate that class and configure it and load that XML file and extract those coefficients. so a little bit, just an example that ICE is not only the application, but more beyond the application, and you can dig into more details if you want. So after having those constant shifts, now we are running the resampling again. We say take the geometrical offsets that we did, or that DM assist offset, whatever you call it, and also account for these constant shifts that we talked about a few minutes ago, and do resampling again. So basically a more precise resampling between the reference and secondary images. And that's going on. So I think, how are we doing with time? It's 2:30. Is Paul, I assume Paul is in the meeting. So Franz and Gareth, what do you guys think? I have another notebook already pre-run. I could just more quickly go over them, different steps. Is that a good idea?
Is that other notebook, is it essential for the homework?
Well, it's the same notebook. I have gone through all the steps.
Oh, okay. Yep.
So do you want me to go just over that one maybe?
Yeah, let's go just over that one so that people can go on and to start with the homework exercises.
Okay.
We don't stretch people's.
And in the meantime, people can click away in their own ones to run it to the end.
Yeah, so you can go ahead, those who are able to run, you can go ahead and try to run it to the end. Well, it's the same notebook basically, but I have run it before, just maybe based on experience of teaching this course. It's possible sometimes that we don't have enough time to go through all the steps. So sorry for scrolling. I'm gonna get to the point that we just left off right now. All right, almost there. Geometry we did, resampling we did, and we did the misregistration. And here, yeah, okay, that's the misregistration. And refine resample we did actually. So we did refine resampling. The corresponding SLC is there. And then the next step is dense offsets. Now we say, okay, the two SLCs are resampled pretty good now, but now we are interested in any detailed pixel shifts, pixel offsets between the two. If somebody wants to, actually, we have turned this off in this notebook, so it doesn't go through it. But as you will see in one of the modules, Brent Minchu is going to talk about using offsets, pixel offsets for some applications, mainly for cryosphere. Then that would be this step basically. If we would run this, we would get to some dense offsets. Apparently, I have done that actually in this run, but yeah. And then we get finally to the interferogram step. We have run all the co-registration. Now we just cross multiply and we form an interferogram. So that's the step that the magic of interferometry is gonna happen. When it's done, then we get a directory called interferogram, where we have multiple files there. The interferogram itself is going to be here, topophase.flat. That means an interferogram that is already flattened for the geometrical phase. We have the correlation, and we have the same layer but at full resolution, and also the amplitude of that interferogram. For the ionosphere session, we will get back to this. If we want to do ionosphere, we want to run the subband. We want to make few more interferograms. We will get there. Don't worry about it for today. The interferogram might be noisy. and that may make phase unwrapping a little bit difficult. So the smoother the images, the unwrapping is usually easier. So usually it's a common practice. If people want to, they can filter the interferogram before phase unwrapping. But you really have to be careful, of course. Filtering means changing the data a little bit. If you want to go to more details. So here is the interferogram. We have the island, that's the magnitude of the interferogram. And here is the wrapped interferogram before filtering. And here is the multi-looked filtered phase of the interferogram. If we zoom in a little bit to that area where we had a dike opening, I think somewhere, 2011. This data was 2011. So there was a dike opening, and that is very evident in our interferogram. If you take even a closer look, this is actually a beautiful interferogram. You see all those fringes, and they are meaningful. Probably Franz and Gareth at a different occasion, if you want to, they can probably talk to it a little bit more than me. I'm sure more than me. But yeah, we have an interferogram that has a geophysical signal there. And from Gareth, can I ask you, the fact that we have more fringes on this side compared to this side, what does it tell you?
It's because of the geometry.
All right. So yeah, it's not a vertical dike.
It's not entirely vertical, but also it's partly the acquisition geometry that's giving you the asymmetric pattern.
Okay. So yeah, absolutely. So yeah, then that's the tricky part that comes in, that whether, okay, is it, how much of it coming from the SAR acquisition geometry? And then if you have another geometry, then you could constrain. I'm sure Gareth somewhere, either he has talked about it, or I think somewhere you will talk about those geometry stuff. Then you can constrain what's the geometry of the model that you are looking for. Anyway, more steps, that is not your concern. We will get back to those steps in the ionospheric phase estimation. And finally, the phase unwrapping. If you run phase unwrapping step, those wrapped phases is gonna get unwrapped. And here is the result. Here is the wrapped interferogram, and here is the same interferogram unwrapped. And here is one quality metric that we have found it to be very, very useful. It's called connected component. It's integer between 0 to whatever number of connected components you have. In this case, it's very useful that in this example that shows you that connected component 0 is actually over ocean. So already when you get an interferogram, you could just mask it out with connected component 0. And for the rest of the connected components, it tells you it starts from the largest connected component is the one basically that has the largest size. So that's 1, and then it goes on to whatever connected component that you have. So this is an easier, much easier interferogram to unwrap, even though we might even actually have some problem where the dike was. But in other cases, you will see by experience that, yes, thank you, Franz, the software that we used for this unwrapping here is a snafu. And when we have multiple connected components, then in an interferogram, then that also is another challenge, how to connect those connected components and get a final interferogram. But anyway, I think the lesson that you should learn from this, and we always revise it ourselves as well, is just trust connected components more than where trust the unwrapped interferogram where the connected component is not zero. And when you have multiple connected components, be careful and pay attention to the discontinuities between. Imagine if I have an island here, if I had another island. Actually, for NISAR, that would be a case that our SWAT is going to be 250 kilometers. We probably covered the entire different volcanoes in Hawaii in one frame. Then how are you going to connect those, right? How many fringes are between? We usually, it's not very easy. And sometimes you need just extra information. Sometimes if with some assumption you might be able to connect them, but sometimes it's just not possible. So just a little, that was a little bit about the challenges of the unwrapping. What happened in 2D that you saw, if you look at it in 1D, here is what is going on. Basically, we had some wrapped phase. Look at this one. This is the wrapped phase. This is a profile over some portion of the interferogram, a 1D profile. You see the phase is changing between minus pi and pi. And if you look at the unwrapped phase, you see that actually it's just going, it's the same pattern, but whenever we have a 2 pi jump, it adds an integer number and basically unwraps it. So that's why the unwrapped phase looks smooth like this one. And in this case, we never had a 2 pi jump, so the unwrapping didn't do much except for the shift that's always there. But otherwise, the pattern is the same because over this region, we didn't have 2 pi jump, right? So unwrapping didn't do much. The difference is just a couple of 2 pi jumps. So by the way, the phase unwrappings that we are using and is always our favorite is only those algorithms that don't change the data. They only add or subtract 2 pi jumps. So you can always take out the 2 pi jumps and get back to the wrapped phase if you don't trust the unwrapping and redo something of your own. All right, so I am almost done. The geocoding is the last step that you could run, and basically all I showed you was in radar coordinates. You can run geocoding and basically align to the map coordinates. Now it's more consistent with what you would expect. That's part of the island. The dike is here. All right, there is some supplementary information in this notebook about the XML files. If it's your first time dealing with XMLs, this might be useful for you. And the configuration file that I showed you and was in the notebook basically was very simple. It was basic, but there are many more options that you could play with. And you could, for example, region of interest that I mentioned, change the range, the number of blocks, change the posting if you want to, and filter strength with a number between 0 and 1. You can change the filter strength and see how the interferogram changes. If you have a different DM, high resolution, if you change if you want to unwrap at all or not, they don't want to unwrap for some reason, you can turn it off. The unwrapper name could be SNAFU or ICU. The do rubber sheeting, I'll get back to that in the ionosphere session. And yeah, the same. Do dense offsets. If you want an image of the pixel tracking or speckle tracking offsets, if you turn that on, it would run that step for you. And you can set up the configuration of the cross correlation with what's the search window size, what's the skip size, what's the window width size, and what are the files that you want to geocode if it's not already geocoded. Do dispersive, it's for ionospheric phase estimation. And you can have more control on the filter of the ionosphere I'll get back to that later. And the sensor names. What we showed you today was the configuration for LOS1, but if you have other sensors, here are some examples. For example, for NVSat, wherever you see master, please change it yourself to reference. Sorry about that. I should have done that. It should be reference and secondary. Otherwise, there are examples of the Sentinel-1, LOS2. So if you have any of those data set that you want to take a look, you could change the sensor files, the reference.xml and secondary.xml, and run it through your data set. So that's all. And one example down here is just, again, another example that you could use ICE as a Python library. You can import different modules, and this XML file has almost all the metadata. Actually, all the metadata that a SAR image should have is here, and by loading it, you have access to it. And once that is done, then you have access to, what's the time of the middle of the frame, and what's the velocity, what's the PRF, pulse repetition frequency, and what's the, and you can roughly estimate the azimuth pixel size, or you can extract the slant range pixel size, or another example. So I think that's all I have. If there are questions or not, I think the homework for you guys for this notebook will be change the configuration, try to change, well, first of all, you have to run this notebook really. It's going to be very helpful, even though if you are not interested in processing any strip map data and you want only TOPS data, I think it helps a lot to start with strip map data. It's much simpler workflow. So run this notebook, change the configuration as you wish based on what I showed at the end of the notebook, and change the data set. That will be the best exercise actually. Just go on the ASF website and find the data set that you want to try. There are a lot of other LOS1 data sets there that will help you to make sure that you can find the right data set to process. So choose your area of interest. A couple of you can help each other and process through one pair of your own data. That will really challenge your skills on learning this software. So I'll stop sharing since we are really behind. Any question?
Yeah, there's a question at the very bottom. I'm not sure if you see it in the chat.
Okay, if you want to do a batch processing and want to crop at SLC, not raw data, how do you input that on the XML file? So batch processing of one page, you mean? Is that what you mean, Rodrigo? Batch processing of one pair? Or you're thinking about stack processing?
Seems like it might be a stack.
Yeah, you have, in this case, he says yes. If you are thinking about stack processing, then this application was only for one pair. But on the last day, we will point you to the stack processor, which really is extending whatever I explained today to a stack of strip map data. If you are thinking about doing the same process, but in batch, then you have to write your own workflow and the region. But if you just want to crop and run this on one and one subset, yeah, you can put in region of interest. If you want more than that, if you are thinking, okay, I want to process one pair, but in batches, then you have to write your own workflow. It's more work than just changing a parameter. All right, anything else? I see you are back, Paul.
Yes, I'm back. You went so long that I even finished my other meeting and came back. I'm pleased to say that I was the least over of the time slots.
Yeah, well, I didn't run through some of the salts. So.
No, I know. There's just too much material. We never learn. I think we go over every year, but it's great to get an overview when we have time for the homework in the office hours and the homework review in the morning for people to ask questions. So hopefully it all works out. Thank you for your time, and thanks to the other instructors as well. I think at least a few people said they were happy about the presentation, so maybe people are not too upset. And of course, those who had to drop off because it's like 3 in the morning, they can go back and look at the recording. So great. Okay, so I think we have coverage for the office hours this afternoon. I think Franz and I cannot do it since we have another meeting, but I think Gareth, you'll be there, right?
I will be.
And I'll be there tomorrow morning at 7. So I personally will see you tomorrow, everyone, and have a good evening. Thank you very much. Any final words from other instructors?
No, thanks for hanging in there.
Yeah. Very good. Talk to you later. Bye-bye.